Requested today's speaker. The tomorrow we have one more session. We requested Dr. Satya Sekhar. He's great and accepted, and he joined today. He like to handle today's sessions 3 and 4. So little modification in this things I like to share right now. So I welcome Dr. Satya for joining us this meeting. It is an honor. So I'd like to introduce him. Dr. Satya is currently is an associate professor and holding the HOD of Department of Mechanical Engineering at IIT Jammu. He is an MTech and PhD from an IIT Guwahati. Worked on this hydrogen storage and is taking some couple of projects and doing his research work. One of his recently passed out his PhD student. He's got postdoctoral fellows, I think, in Japan. Dr. Uday, right? Satya Sekhar?
Yes, sir. Yes.
Is having a quality of the research work. So he's the right person. So with this small introduction, I hand over the session to Satya. Please take this session. Over to Satya Sekhar.
Is it my slides are visible, sir?
Yes, slides are visible, audios are very clear.
Yeah, thank you so much, first of all, for giving this opportunity to talk about integrated hydrogen energy systems. Good evening to all. So, thank you so much for joining this session. First, let me introduce about our IIT Jammu. We have started in 2016. We call that is third generation IIT because, as you know, many of you, first generation started in 1950s and 60s. Then second generation started in 2008 and 9, and third generation we are started in 15 and 16. So we have around 400 acres on the highway of Jammu to Srinagar, but we are very close to Jammu, just 16 kilometers from the airport. And we are the second best NF ranking in third generation IITs. Now, going to that hydrogen electricity and energy economy, I'll introduce about present fragile energy economy, then energy and CO trends. Then I'll also talk about hydrogen electricity, like clean secondary energy carriers, then elements of hydrogen economy, then suggested future energy economy based on the hydrogen. I want to quote here from Jules Verne, what he said in 1874: hydrogen from water alters to replace means water will be the coal of the future. That's what he predicted in 1974, but now we are witnessing the same. As many of you know about the global environment challenges, I think maybe the previous speakers also talked about this regarding this climate change, how we want to reduce the CO2 emissions. We have global agreements, COP21 and Paris 2015, to reduce the global warming less than 2 degrees compared to the pre-industrial levels. And also we have the problems with air quality, like currently in Delhi, we have too much air quality problem, and we want to regulate the NOx emissions, and also we want to restrict number of the commercial vehicles in future. The third important is the renewable energy development and also energy security. I think you have seen, I think last 2 years we are seeing the lot of geopolitical situations, the wars between the different countries, and it is depend upon again energy security. Some countries, because of the energy problem, they are unable to do something what they want in terms of energy. So every country want to be independent of like energy. Don't want to import or depend upon other country based on the energy consumption and demand. So that's what we want to diversify our energy sources and also improve the renewable energy development in our country. So based on this, the automotive industry is facing challenges, as well as it will also have some opportunities for the new technologies in the automotive sector as well as the power sector. So basically we want to phase out of fossil fuels process based on the two. One is phase out of fossil fuel vehicles, then phase out of fossil fuel power plants. So these are the two steps we want to follow to reduce the CO2 emissions, and also we want to go for the renewable energy development. This is our global primary energy demand. We started with 19th century, how we started with biomass, and we expanded the energy demand consumption by using coal and oil in 20th century first 50 years. Then sudden increment in the energy demand by because of the standard of living increased in Western countries. Uh, then after that, China took the industrialization. The most part of the demand came from the China from 2002 at currently. India demand also increasing day by day, and it will still will increase next 15 to 20 years, the Indians energy demand. So that will give the demand for the total energy demand of the global. The, then we want to increase the renewable energy and decrease the fossil fuels. If you see, after 30, it was predicted that the fossil fuel energy consumption will decrease, and the part will be compensated using the renewable energy. Here, just I want to show the energy balance of the traded fuels. If you see the 1990, some countries are deficient, energy deficient countries like USA and European countries, especially the South Asian countries also. But in 2017, the US become a surplus country, and Russia is always surplus, and some other countries always deficient, like the European Union as well as the our Southeast countries, in the East countries. So if you see our India energy imports, if you see 2021 and 22, we imported almost $620 billion, and it was predicted next year. I think we are going to import around 22 lakhs crores oils, or the minerals, fuels from distillation products. If you see in that, we are at least importing 30% is related to only that fuels and oils, distillation products in the Indian imports. So if you want to reduce at least 5 to 10% of this one, then we can save a lot of this currency exchange between the dollars and Indian rupees. So in I think 2021, Prime Minister Narendra Modi ji said green hydrogen will play a significant role in achieving India's decarbonization goals. He also announced the national ambitions to become a global hub for green hydrogen production and export. So then people think that why green hydrogen is must for India. So as I said, we have energy import reduction. We want to reduce the energy import reduction by going with respect to renewable energy. Then also we have plans to increase the renewable energy up to 500 gigawatt by 2030. Currently we have more than 100 gigawatt, but we want to go with 500 gigawatt by 2030. Then we want to become again by 2070, we want to be carbon neutral. Then we want to be also carbon clean energy later, because we are the third largest CO2 emitter. If you see that green hydrogen will also help to reduce our import bills, like you can also reduce the carbon, crude oil, natural gas, because these are we are using for a different purpose, either for industry or transportation, in different ways. So if you go moving converting from this to hydrogen, then and produce hydrogen within our country, then we can reduce the import figures. You can see that these are the various figures related to different fuels. So the green hydrogen will help in twin goals of energy security as well as the decarbonization. If you see, only 18% of the total energy consumption in the form of electricity, the remaining 82% will be in the other form of energy, like not electricity, maybe in the heat or other ways. Like we want to have, if you want to have deep decarbonization, then you have to reduce the 82% of energy, like the in that imported depends of oil, coal, or gas. And if you see that the number of carbon atoms to hydrogen, slowly we started with wood, and it is like 10 atoms per carbon to 1 atom of hydrogen. Then we are moving to coal, 2 atoms of carbon to 1 atom of hydrogen. Then petroleum, 1 atom of carbon to 2 atoms of hydrogen. Now we are moving to CNG based IC engines, one atom to of carbon to 4 atoms of hydrogen. Then if you go for pure hydrogen based transport or cars, then you may have 0 atoms of carbon for 2 atoms of hydrogen. It means that towards we are going to reduce this carbon to hydrogen ratio, and we want to make it zero at in the near future. This is, I think, many of you know what is the global potential of various energy sources. If you want to reduce the fossil fuels, then obviously you need to have other kinds of energy sources like solar, wind, and nuclear. That we have to develop the technology to improve the energy production from other side. Now we have a goal of around 500 gigawatt by 2030 related to renewable energy, and you can see that the localized cost of electricity drop related to different sources. We have like onshore wind, it is decreased, but the slope is less. But you see the large slope reduction of the price in terms of solar photovoltaic. In 2010, the cost is very high with respect to wind, but currently it's very cheap. So currently some projects we are getting 2 rupees to 2.5 rupees in India. So that will give the like major push towards the renewable energy with respect to solar photovoltaic. This will give a major advantage to reach that 500 gigawatt renewable energy by 2030. And we have some offshore the energy also. This price is coming down, but still it is higher than the solar photovoltaic. Then another, we have renewable energy source, that is concentrated solar power. So solar power, the price is coming down, but still it is 2 to 3 times higher than the solar photovoltaic. This is mainly because of we don't have a large mass production of these components of concentrated solar power. But the technologies are improving, that we are getting new technologies. Maybe I will talk in the next session about the concentrated solar power, how to improve the technology and how to we can reduce the price in the near future. Basically, we have very cheap electricity which are coming from solar photovoltaic. That how we can use this energy with respect to increasing the surplus related to India's grid. Now, suppose if you have maybe 450 gigawatt by 2030, then what will be the problem related to the grid? See, you cannot achieve this 450 gigawatt like without production of hydrogen with respect to the grid. Because just I am giving some example here. It is the problem related to California. You can see that in 2012, this is the energy demand curve with respect to per day. So this curve is almost constant, but a steep increase in the during evening hours, maybe like 6 to 10. But if you increase if you go by year by year, the demand in the daytime is going to decrease. This is because the many houses, installed the solar PV. So they may have a two-way metering. It means that they are not giving the demand to the grid during daytime. So they are giving that their own solar PV production electricity. So you can see that at the end of 2020, so the energy demand is very, very less during daytime of like sunshine hours. Then it's a sharp increase in the evening time. So this problem, to address this problem by using this 450 gigawatt, if you have in grid, then it will be very big problem for the national grid. So to address this one, and also at the same time, you are getting very cheap electricity, at least like 2 rupees per unit electricity. Then you want to get this advantage of low price, and also you have a problem with the intermittency. Like you can only get daytime with respect to solar PV. Then how to manage the grid? That is the major problem. That's why we call this is the duck curve challenge. So in order to handle this cheap electricity and also grid, that will be a major trouble. I think major task with respect to grid by 2030. The tackling the global warming, we have a demand side. See, many we are like technology development with respect to efficiency. The efficiencies are improving, like air conditioning the stars are now the technology COB is increasing, and also other appliances also we are increasing the efficiency. It means that if you increase efficiency, also you can reduce the CO2 emissions, because your if you increase the efficiency, then your supply demand is going to decrease, so that you need to not to like produce too much electricity, so that your CO2 emissions can be decreased. That supply side, uh, again, as I said, we are going to the renewable side. By 2030 we want to have 500 gigawatt. Then you can also decrease CO2 emissions from supply side. Then adaptation, we have to have some strengthening flood defenses to adapt the climate change, that we should take care to reduce the CO2 emissions. So, like the projected CO2 reduction from various sources, if you see this contribution to CO2 reduction by 2030, this is the predicted one. So, the major is chunk is coming from the mileage, means transportation, predicting that we will reduce CO2 emissions 35% from the transport side, and 13% is coming from the energy production efficiency, and 30% is coming from lighting, ACs, and industrial motors, improving the efficiencies, so that we can able to decrease the CO2 emissions 30%. Then 10% improvement if you go with respect to large scale nuclear energy. India having lot of future plans, so we want to increase this 2%, 3% of nuclear energy to 10% by 2040 or 2050. Then 12% which are coming from the renewables and biofuels. Just I want to give here how this regulatory policies for internal combustion is working. You see, the European Union agrees to cut 30% of trucks and bus CO2 emissions by 2030, and Norway, they want to ban this like combustion engine vehicles from 2025. Again, this is again the policy. So, and again, China having different policies to reduce the CO2 emissions, and also how to reduce these combustion vehicles. Similar way, Korea also having to ban this diesel engine vehicles from 2030, and you can follow similar policies to reduce the CO2 emissions with respect to the transport sector. Then what is the replacement of oil for the transport sector? That is the major important task. So natural gas currently using for some vehicles, and but still it's not a long-term solution, because we are importing the natural gas, and also the CO2 emissions also still some emissions still it's, but it's better than diesel and petrol. Then we have a second generation biofuels. Basically, this will impact on food situation, because the same land you cannot use to produce the biofuels instead of food. Then impact on environment, like if you increase the production biofuels, then you need land of like cutting forests and use of fertilizers, and irrigation also may be one of the problem. Then we have other two options. One is electrical drives by using lithium-ion batteries. Then the hydrogen as a fuel, like non-fossil hydrogen, will be the one of the options. So in future, you will see the two types of vehicles after maybe 2030. One is electrical drives using batteries. The second one is hydrogen as a fuel. So this is the green car strategy with respect to the fuel economy improvement and hybridization. Currently, we are going with combustion engine plus electrification. Then future, the only electrification will be there in cars. One is either will work with hydrogen or will work with electricity based on the batteries. So the R&D is pushing towards the clean mobility with respect to battery vehicles and hydrogen fuel vehicles. Now the both type of cars are running on the road. You can see Tata having fuel cell vehicles, and battery we have many different companies are manufacturing currently. This is again important thing to like what is the global demand by electric vehicles, how it is affecting the oil demand. See, you can see that in China, as maybe you know that their production is very very high in terms of usage of electric vehicles. So if you increase the electric vehicles, the energy demand with respect to fossil fuels, petroleum or diesel, it is going to decrease. Means the imports which are not same pattern compared to 10 years back of China. So the percentage, the number vehicles are increasing in China. At the same time, the energy demand or import is not decreasing at the same time with respect to same slope, because they have increased the number of battery vehicles. It will affect obviously the oil demand. So that is very important. Once if you move towards the electrical based vehicles, then obviously your energy demand with respect to fossil fuels is going to decrease. But uh, still we will increase the still our demand will increase with respect to fossil fuels, because our number of vehicles is going to increase again still 10-15 years. So but the percentage will be, some percentage will come from the electric vehicles. So the same demand or slope will not have after maybe in 10-15 years. So that will give actually the global oil demand will going to decrease if you go to increase the electrical vehicles all over the world. Then like you have a different technologies, then how to choose which kind of vehicle you have to use. So as I said, we have batteries vehicles, we have fuel cell vehicles, conventional ICE engines at the same time, and like hybrid vehicles like batteries and ICE engines. Then you have to think about cost versus operating cost. Like initial cost is how much and operation cost is you have to vary with respect to your ICE engine as well as the battery vehicles. In some states the electricity cost is very cheap, so in that case even the cost of EV is high little bit compared to ICE engine. But at the same time, if you have a long term like 15 years 10 years, then the total cost of the initial cost plus operation cost will be very less in terms of EV compared to your ICE engine. That is depend upon again your state and the cost of electricity, and related again the government taxes and regulations we have to see. We have again fuel cells and batteries. This combination also we have hybrid things. Yeah. Then we have to see how we can see the energy storage comparison, because this is the important. Like a vehicle is has to run like 1,000 kilometers or 2,000 kilometers. That depends upon your specific storage capacity. But if you compare like different types of batteries, like lithium iron battery, we have like storage capacity around 150. But if you store the 1.64 kg of hydrogen, then your specific energy storage capacity will be 580. Then if you go for other type of battery, it's 200. Then it is around the hydrogen will give this same specific energy 2 times, 2.5 times more than that one. Then we have other batteries. It will the storage capacity is going to increase 2-3 times more. So this will give the additional advantage. Like suppose we have new applications that UAVs, drones, underwater autonomous vehicles. Those we can use this kind of hydrogen based vehicles, so that we can improve uh, in the endurance, the flight endurance. We can improve at least 2.5 times compared to batteries. Then if we see the total cost of the ownership with respect to vehicles, so you can see that your battery based vehicles already coming down, and it is going to near to that ICE engine based. The hydrogen vehicles also will come down. The cost is very high now, because the R&D cost is too high, and also we have to go for mass production. Then only the cost will come down with respect to the battery vehicles. If you see the like we have different types of production technologies, like electrolysis of water and electrolysis of carbon dioxide to carbon monoxide, and we have biomass gasification, char alkalic process, and the reformation of fossil fuels with CO2 sequestration. Then we have a coal gasification to produce syngen gas to produce the hydrogen. Currently we are using mostly with fossil fuels. We are producing hydrogen in India as well as the abroad, all over the world. But if you want to go to that green hydrogen, which is coming from the energy has to come from the renewable energy sources. So that we can give the production by using the electrolysis of water will give the big jump to the hydrogen production. At the same time, in India also we have different technologies like biomass gasification, also one of the future technology which can give the low press hydrogen production. And you can see the fuel energy densities and sources of hydrogen. So hydrogen, as you know, it's very high specific energy compared to the other energies, other like petrol or diesel and LPG. And you can see that how we can produce hydrogen with different efficiencies, energy requirement. See that methane reforming, it is, we can get 65 to 70% of hydrogen production efficiency, and you need like 41 kilowatt hour to produce 1 kg of hydrogen. Then electrolysis, we have 51 to 71%, and it is a huge requirement of energy in terms of kilowatt hour, like 50 55. And coal gasification, the efficiency is 45 to 65, and you will get the like you need energy at least 51 to 74 kilowatt hour. And the biomass gasification efficiency is 44 to 42, and the energy demand to produce 1 kg of hydrogen from the 40 to 44. So you can see here how current commercial hydrogen generation process. You can see the most of the hydrogen is produced through fossil fuel. Only very 4% we are producing using the renewable energies. So this trend has to reverse. So we should able to produce the hydrogen using renewable energy. So that we call as green hydrogen, and other fuels, other methods is going to decrease in future. Like in steel industries already started to produce hydrogen through renewable energy sources. And by using the solar energy, how we can produce hydrogen, we have a different ways. So if you use the heat energy by using thermolysis, we can able to produce hydrogen. Then we can also use the wind energy. Means again, the wind is in terms of in solar and other hydrogen renewable energies, we can produce mechanical energy, then use electricity, then use, you can use water electrolysis to produce the hydrogen. Then biomass, again we can have a conversion to hydrogen by using biochemical or thermochemical routes. Then we have photo biological and photo electrochemical. The photolysis also you can produce hydrogen. So you can see that how we can convert the solar energy or renewable energy into hydrogen by different ways. So current cost of Indian unit of hydrogen, uh, these are like based on different technologies. Suppose you have a steam methane reform process, you are able to get 1 kg of hydrogen for 180 rupees. But this is based on the like we have taken, this is produced 10 ton of CO2 per 1 ton of H2. So byproduct we can get, we will get 10 tons of CO2 per 1 ton of hydrogen production. This is the major drawback to produce hydrogen through steam methane reformation. So currently it is, the price is low, but still it is not a future aspect, because we have problem with the CO2 emissions, and again the import of oil. And biomass gasification, it is currently at 280 rupees, but the problem is the raw material supply chain issues. Electrolyzer, the cost is high, now around 400 to 440 rupees per kg. But this is again considering a power cost 3 rupees per kilowatt hour capital cost of electrolyzer of 5 lakhs per meter cube. So cost will decrease if you able to decrease the capital cost of electrolyzer 5 to 1 lakh per meter cube, maybe in next 5 to 10 years. So the technology is major driving in India. So many people are playing now, coming with respect to new electrolyzers, which can reduce the capital cost to 1 lakh per meter cube. So that is the next 10 years goal, to reduce of hydrogen by using the electrolyzer. Then photoelectrochemical, this is a very high cost because it's having very low conversion efficiency. So this will not be have feature scope to produce hydrogen at low cost. Then coal gasification, we have the cost is very low, but like again India has rich amount of coal reservoirs, like, but it will give some kind of CO2 emissions that will hamper the, again, our goal to reduce the CO2 emissions. This is the global hydrogen cost. If you see with respect to different countries, cost of hydrogen in Paris, it is 6 euros per kg, and in China it is $5 per kg. Again, the government subsidy. And the cost of hydrogen in South Korea, it is around $7.4 per kg, and the cost of hydrogen in Japan is near $10 per kg. So why I'm saying this cost of hydrogen in UK 10 euros per kg? Because again, so we want to become a global hydrogen, a green hydrogen hub. Then basically we want to export. If you're able to produce cheap electricity, cheap hydrogen within India by using renewable energy, so this will give the driving force. Like if you have a production cost is half of this cost, then you are able to produce means transport to other countries, not only using in India, but you can also export to other countries. That is the major goal by 2030. And you can see the cost of hydrogen we are expecting to decrease with respect to the like future, like 2030 it is going to have off cost of like 6 euros per kg and 2 euros per kg. It is going to decrease with respect to mass production. So that will give major advantage for India. Like to at the same time, you will reduce the import cost, and also you can able to export the fuel to other countries like near countries like Singapore, Japan, so that we can able to reduce this import burden to our Indian economy. Uh, Again, the fuel cell electrolyzer, these are like making these systems, it is like a multidisciplinary approach. So one person cannot make this kind of system. So you need multidisciplinary people, like from starting from material science people, chemical, and also you need mechanical, and also you need electrical people. So we have like composite materials development, and also we need to have power control unit, like we need DC converters, DC AC converters, and we have a stack heating and cooling. So there we need thermal people. We have a reaction and cooling and air supply. This is also related to engineering. Stress analysis related to biopolar plate, other plates. Then design people will come into picture. Then membranes related to electrodes. These are like chemistry and chemical people and metal science people who work on these different aspects of electrode chemistry. So basically, this what I want to say is it's a very highly multidisciplinary area. People can work different people and can have a produce very high efficiency fuel cell system or electrolysis system. uh, you can see the basic components of the fuel cell system. So we have a boost converter to convert the voltage requirement to the voltage requirement for the your motor or battery. Then we have a fuel cell stack that can produce electricity by taking hydrogen, and we have a water separator because uh, your end product like using electricity, and also you will get some water vapor outside. Then you have a boost heater to increase the temperature. Then we have some cooling pump, because maybe I will tell how we need cooling in fuel cell system. Then we have a humidifier and air compressor. Then we have a recirculation fan, and we have ion exchanger, and the entire body of the fuel cell and air compressor. Uh, so these are various components we need to have for fuel cell system, including stack. This is a schematic of fuel cell hybrid bus. You can see that we have like hydrogen storage in the cylinders around 40 kg capacity, and we have a lithium ion battery. Yes, because maybe fuel cells will take some time to start, and also some peak time you may not get enough power from the fuel cell. So in that case, you have to go with respect to the you have to take some power from the battery. Then we have motors which can run using the electricity which are generated from fuel cells, and you have air compressor, and this is the energy management which can take control the electricity generated from fuel cell and as well as the battery. So here you can see that 120 kilowatt the fuel cell system which will drive the motor of the your electric bus. Now we may have a doubt what is the difference between the battery and fuel cell. Basically, both are electrochemical devices. The only difference is the fuel cells we need continuous flow of chemicals, whereas in battery we already store the chemicals stored inside, so that can convert into electricity. Then the other difference is fuel cell will continuously produce electricity as long as you supply the fuel, whereas in battery, if it will goes dead, again if you have rechargeable battery, then you have to recharge again, so it will take some time. But the fuel cell will continuously supply electricity as long as your fuel is going to supply. That is the major difference between the battery and fuel cell, because both are electrochemical based devices. Here you can see how we are converting hydrogen into electricity. So basically, this fuel cell will convert the chemical energy from fuel directly into electricity, not like your like IC engine. So you will convert first chemical energy into thermal to mechanical, mechanical to again you can, if you able to use in electricity. Whereas the fuel cell will convert directly chemical to electricity. Because of this direct conversion, you are able to get very high efficiency compared to IC engine. Then very low noise because there is no moving parts here compared to our IC engine. The stable power generation, you can continuously produce power from the fuel cell. Reduce expensive power transmission because you can able to change the requirements based on your stack, so that your stacks can be like connected in series or parallel, depend upon your power requirements, and less polluting. You can see hydrogen we are supplying to anode side, and it will become proton and electron. The electron will flow through the your electron circuit. The proton will go through the your membrane, and it is going to again cathode. Other side we are supplying oxygen from the air, so this will again cathode side will mix. Again, we have electrochemistry here. Then we will get the air and water vapor from the outside. So basically, you are getting two outputs. One is electricity, second is your water vapor. At the same time, during this reaction, we may get some heat output. So that heat output depend upon your temperature. You can able to use for other applications. That I will tell how to use that waste heat which is coming from the fuel cell. So basically, we are getting electricity, and byproduct you are also get some heat output depend upon the types of fuel cell. So this is how we are converting hydrogen to electricity. Then that the difference between the fuel cell and the battery, like how much energy storage volume is required, how much kilometers we can range we can improve through battery and the fuel cell. See here you can see the difference. The batteries, if you want to have more miles, then your volume requirement is very high. It is the slope is very high compared to the fuel cell. What it means is, if you are increasing the range, number of kilometers, then your battery volume is requirement is very high. It means that maybe sometimes you may have to add one more truck to carry the batteries to run your big truck, which is going to have 1000 miles or 2000 miles. But if you see the difference with fuel cell, the volume is not increasing as much as the battery. So your number of miles of the truck will go slowly, means the volume will increase less compared to your battery. So that this advantage will give to fuel cells which can go like trucks are going 1000 miles per day or 2000 miles. That can be used for the fuel cells. The advantage of lithium ion batteries, obviously, these are cheap and technology is readily available. Suppose you are going to have using your car within your city or maybe 200 kilometers. Obviously, currently the battery based vehicles are better, but vehicles which are going like long range, then obviously you cannot wait for the recharge like 3 hours or 5 hours 6 hours. Then in that case, the fuel cell based vehicles are better, like for trucks. Especially you can recharge the fuel cell truck within 5 minutes compared to the battery. And maybe in the next year, maybe starting of next year, in India also we are starting the fuel cell based trains. uh, I think it is between Jind and Panipat. The first fuel cell based train is going to launch between Jind and Panipat by next year. So this will give advantage of the fuel cells if you need very high power requirement in the vehicle, and also if you want to go long range compared to the battery. So battery for the low range and fuel cell for high range vehicles. Again, why this hydrogen deserves attention? I think some people knows that We started the fuel solids like wood we have used, coal. Then slowly we converted into liquids, oil, petroleum. Now the trend is we are going to have these gases. Okay, so this year maybe its predictor is wrong, but still, but the this trend is same. So we started again. We are going to natural gas. Then after that we are going to have hydrogen in future by 2050. So that will give advantage with respect to hydrogen. Why we are choosing hydrogen future fuel? Because hydrogen is the small most of all atoms, and also it is having a very high energy content per weight, like 3 times of gasoline. And but the problem is that it has having very low energy density per volume, so requires large storage tanks with atmosphere pressure. But this is going to handle problem with respect to with we have other technologies which can reduce this problem to handle this low energy density per volume. So this is the predicted world hydrogen economy. So you will produce hydrogen by using renewable sources and nuclear energy. So that will be used for transport and storage. Then you may use for combustion or fuels, fossil fuels, fuel cells. So that will give you the useful energy. So basically, you are taking water from the environment to produce hydrogen, and by producing hydrogen, you will release oxygen in the water. Then again, for either in fossil fuels, fuel cells or combustion, you will use the same oxygen which is delivered here to produce hydrogen. So again, you use same hydrogen and oxygen, get the useful energy, and you will release again water vapor to the environment. So cycle will continue. So without releasing any harmful gases to the environment. So this is the future world hydrogen economy. So as I said, if you see the fuel cell electrical vehicle, we have different components. Like you need to have hydrogen storage system, then you need to have a motor, and also you need to have some PEM fuel cells which can generate electricity using the hydrogen. And you need small battery because you may have sometimes initial startup time you may need very high power. Then in that case we will use the battery, and also you may need sometimes the peak the power fluctuations which cannot take tackle by fuel cells very instantaneously. In that case we will use the energy from the power from the battery. So battery will give like small range power which can use the tackle this fluctuations in the power requirement as also in the starting point. So but when you are cruising that vehicle, then we will charge the battery using the fuel cells. Okay, so then we need to have a small battery and big fuel cells for hydrogen based electrical vehicle, because other parts related to same as like a EV vehicle only, except uh, we have a battery and small battery and a big fuel cell, and also we need to have hydrogen storage system in the electrical vehicle. uh, like we have a different types of fuel cells for a different purpose. Here I have given I listed here proton exchange membrane based fuel cell which can work in the range of 80 degrees, and other fuel cell we have a direct methane fuel cell which can work again for 80 degrees. So here you can give the input uh, in different forms of energy, but in PEM fuel cell you can only give supply hydrogen which can convert into electricity and heat. Alkanic fuel cell we have this will be range around 100 degrees centigrade, and phosphoric acid it will work like 200 degrees centigrade, and molten carbonate the operating temperature is 650 degrees centigrade, and solid active fuel cell this will work from 700 to 1000 degrees centigrade. So your electrolyte will be different and depend upon your kind of fuel cell, as well as the anode material and the cathode material. So some fuel cells were very good for transport applications, and some fuel cells were very good for stationary applications. Depend upon your application, we will choose the type of the fuel cells. That is very important when you're choosing the fuel cell. Here I'm giving the comparison of various fuel cells as discussed in the last slide. So here you can see the electrolyte of direct methanol fuel cell. We are using proton conducting membrane, and the temperature is below 100. So here we can use the fuel is like methanol. The power range you can like construct the fuel cell in within the range to watts to kilowatts. The application, you can see the vehicles and also small applications where you need very low range power requirement. Then proton exchange membrane, your electrolyte will be proton conducting membrane. Then the temperature is below usually 80 degrees. We will use 70 to 80. Then fuel, you can only supply hydrogen in proton exchange membrane case. The power range, you can generate watts to kilowatts depend upon your application. This is the best proton fuel cell for transport applications, and also small generators, domestic supply. We can able to use proton exchange membrane fuel cell. The alkalic fuel cell, like your electrolyte will be caustic potash solution, and the fuel will be again hydrogen. Same like the watts to kilowatts. This kind of fuel cell we have used many years back for space applications. Maybe in the next slide I will show where you have used this kind of fuel cell in the space application. Then we have another one, phosphoric acid fuel cell. This is again the electrolyte will be concentrated phosphoric acid. The temperature range is 200. Again, your fuel input is hydrogen. The power range is like in kilowatt. You can able to produce. This is like heat and power stations you can able to use because you are able to get 200 degrees waste heat which is coming from the fuel cell, as I discussed earlier. So fuel cell will generate uh, electricity and heat by taking the hydrogen. So this waste heat depend upon temperature where you can use. That is also important because if you are able to use this waste heat again for different applications, then you can improve the overall system efficiency. Then molten carbonate fuel cells, your electrolyte will be like molten carbonate. Then the temperature range of operation is 650 degrees centigrade. This is also very good because 650 is temperature degrees, very good for again you may go for combined heating and power system applications. There you can improve taking the waste heat from the molten carbonate fuel cell and supply it to like organic Rankine cycle or Rankine cycle or maybe Brayton cycle, so that you can still improve the efficiency beyond 50-60%. The fuel we will use here is either natural gas or coal based system. Then like power range, you can go from kilowatt to megawatts. Like again applications like power plants, you can use combined heat and power because as I said, because you are getting waste heat is 650. So this will be very good heat to drive the maybe like power blocks by using organic Rankine cycle or Rankine cycle or Brayton cycle. Then very high temperature application, that is solid oxide fuel cell. Here we will use electrolytic ceramic because the temperature range is very high, like 800 to 1000 degrees centigrade. Again, here we can use pure hydrogen or natural gas. Again, the power range kilowatt to megawatt. So this is also very good fuel cell for the stationary applications where you can get you will use like stationary power generation, like instead of diesel generators you can also go for the solid oxide fuel cell, which can give very good efficiency, and also it can give waste heat at 800 to 1000 degrees centigrade. So this is again you can able to use the waste heat which is coming from the fuel cell to drive other power systems like organic Rankine cycle or Rankine cycle. So this is why we will use this kind of systems for power plants, combined heat applications where you need maybe electricity as well as the waste heat which is at very high temperature. So among these different kinds of fuel cells, major importance we are going to give proton exchange membrane for the transport vehicles and the solid oxide fuel cell vehicles for the stationary applications. uh, Again, if you see the history of the polymer electrolyte membrane fuel cell, see the concept which is started in the 19th century, that is by Sir William Grove, demonstrated fuel cell operating principle in 1839. Around the same time, Christian Sobian demonstrated it independently. Then again, it's reinvented by Francis Bacon, started working on practical fuel cells in 1937. So he has developed in 50s. It's a 6 kilowatt fuel cell. It's a major breakthrough in terms of the fuel cell. It's a great achievement. 6 kilowatt fuel cells in 1950s. Then people used the first practical applications by using the PEM fuel cell in Gemini program in 1960s by for NASA. And again, it was followed by Apollo program, where Pratt and Whitney built fuel cells based on the Baconic patents for the space applications. First vehicle applications, which are like General Motors experimented with fuel cell based van with cells from Union Carbide in mid 60s, but somehow they have not followed up the technology development. So although it was a great success in space programs, but we forgotten this for the transport theoretical application. Again, it was re-entry in 1918 by Perry and Energy Systems, and Ballard demonstrated this fuel cell based submarine. And 1993, Ballard demonstrated again the fuel cell based bus. Now we can see a lot of companies which are working on fuel cell based transport vehicles like Toyota and other companies. So here you can see the fuel cell stack, the fundamentals. You can see this part is related to anode part, and this is your membrane part, and this is your cathode part. See here you have a catalyst layer, and you have a gas diffusion layer, and also you have flow channel. Okay, so here you can see that this is the stacks. We may have different cells we will integrate regarding requirement of your voltage. Suppose you need like 13 voltage or 14 voltage related to connected to the battery, then you have to connect your cells in series when you reach 14 volts power. Then your based on the requirement of the power, you can also increase either in series mode or in parallel mode. If you see the chemistry and the thermodynamics of fuel cells, in anode, as I said, we are supplying hydrogen. This will again convert into by electrochemistry hydrogen protons and electrons. The electrons will go to external supply, then that will be converted into electricity. In cathode side, this hydrogen, the proton which is coming from the electrolyte plus electrons plus oxygen, it will become again hydrogen. So if you see the overall reaction, we are giving hydrogen and oxygen from the air, so it will convert into hydrogen by generating the electricity and heat. Again, if you see the heat of reactions, the if you consider higher heating value around it's 286 joules per mole, whereas lower heating value it is 241 joules per mole. Then if you have the Gibbs like free energy, then it is 237 joules per mole. When you are able to convert into electrical work, so by using this W with respect to electricity, so you can able to calculate how much you are able to convert electricity by using the hydrogen. So this will give the electrical work coming from the fuel cell. Here N is your number of electrons per mole of fuel, then F is Faraday's number, charge per mole of electron, then E is the potential from the fuel cell. So assuming that all the Gibbs free energies could be converted into electricity work, means the ideal work, the maximum cell potential you are going to get, it is 1.23 volt. Means each cell will generate the maximum ideal case, it is 1.23 volt, but in practical we'll get very less, like 0.6 to 0.8 volt. Now if you are able to achieve see the how much energy conversion is happening in ideal case, it is, if you use a higher heating value, we can say that is 83%, whereas if you use the lower heating value for hydrogen, then it is 94%. You can see that these are ideal cases, but in practical we are going to get around the efficiencies from 45 to 50 or 60, depend upon the types of fuel cells. So you can see that how difference with respect to the fuel cell IC engine efficiency. So obviously this fuel cell efficiency is very high compared to your IC engine, but you may get doubt how it is having a very high efficiency compared to the Carnot efficiency. because this is fuel cell is not a heat engine, but it's a electrochemical engine. Because therefore this Carnot efficiency limit is not applicable here, because we are converting the chemical energy into electrical energy without going to like thermal energy again, thermal to mechanical and mechanical to electrical. So the Carnot efficiency limit will not applicable to the fuel cell. Now, if you see that the fuel cell components like solid electrolyte based, like it will have the polymer electrolyte membranes. The role is like uh, it's a solid electrolytes that conduct proton but impermeable to gaseous phase. It means that it can only conduct protons, not electrons. That is the major objective of these polymer membranes. The material basically will use polytetrafluoroethane attached with perfluorosulfuric acids. Basically, this is developed by Nafion by DuPont company. The thickness is very low. It's having only just 20 microns. The properties are required for membrane. We need is high proton conductivity, chemically inert, mechanically strong against swelling. So this is a very good research area for the materials and also chemistry people to make very high efficient polymer membrane. The coming into the electrodes like catalyst layer. So the role is it should have a desired action takes place at this site and current is produced. That is the main objective of the catalyst layer. So material is platinum is the best material so far, but the main problem of the fuel cells, the cost of the fuel cell vehicle, everything is related to this platinum, because the platinum cost is very high. So this is hampering the development, means the cost of the fuel cell vehicle as well as the fuel cells. So efforts are going to develop the low cost alloys that could replace platinum, but still we are using major platinum material as a catalyst layer. Thickness is 10 microns. Less than that could be thinner in the anode side compared to cathode side. So desired properties like you have very high reactivity we need, and the resistance to corrosion and also coagulation because of the flooding problem with respect to water. Then gas diffusion layer, again, this is the layer between the catalyst layer and bipolar plate. The role is uh, it should have like porous layer. It distribute the reactants like hydrogen and oxygen to the reaction sites at the catalyst layers and remove the byproduct. And also it is another important task like electrically it should conduct the correctly catalyst layer and also with bipolar plate. So it should conduct the electricity between the catalyst layer and also with bipolar plate, which is generated by the fuel cell. Then you should also have very high thermoconductivity to remove waste heat, because as I said, we are getting electricity, but we have also byproduct as a heat. So that also we have to remove efficiently so that your fuel cell will not degrade or will not give low efficiency with respect to the time. Then the material we are using commonly is carbon paper of carbon cloth. Thickness will be this is a little bit thicker compared to your electrolyte membrane or catalyst layer, like 100 to 200 microns. May also increase. You can include that microporous layers. Desired properties here, we have high porosity to ensure gas phase diffusion, hydrophobic to help remove the liquid water from the fuel cell, and also high electrical conductivity and corrosion resistance. These are the desired properties for the gas diffusion layer in the fuel cell. And bipolar plate, this is the end plates with respect to the fuel cell, related to gas channel supply reactants and also remove the byproducts. We can use the bipolar plate. Role is to connect outer circuit and drive current between one cell to another cell, and also remove waste heat which is generated by fuel cell. And another important factor is it should provide structural strength to the total cell, so that it will not have swelling during the operation time. Material generally we use graphite is the common bipolar material, and we are also having a lot of research is going to have on coated stainless steels from metals point of view. Thickness, this is the major one which is high thickness in the fuel cell component, that is with respect to 1 mm, so that if you have very high strength and low thickness, then it will decrease the weight of the fuel cell, so that we can improve the we can reduce the size of the total fuel cell compared to the bigger one with using the bipolar very high thickness. The desired properties, we should have high electricity and thermal conductivity of the bipolar plate, and also corrosion resistance and mechanical strength. These are the most important properties with respect to the bipolar plate. As I said, we should also see the water balance, because we are also producing the water as a byproduct from the fuel cell. So you have to remove efficiently water balance, and at the same time you should also be the PEM based fuel cell always should be hydrated. Then otherwise the efficiency is going to decrease. So water balance is another research aspect in PEM based fuel cells. How to remove the excess water, and also how well you are maintaining the fuel cell in hydrated mode. That is important aspect of the fuel cell, PEM based fuel cell. So as I said, again, we are producing the current technology. The hydrogen production is like steam reforming of natural gas. Currently, we are producing 48% globally, and partial oxidation of hydrocarbons 30%, partial oxidation of coal again 80% of hydrogen. Electrolysis, just we are producing only 4% globally, but this number is going to change. This number will going to increase in next 5 to 10 years. Again, as I said, hydrogen is produced from different sources are not same. So like I have given some examples here. We call different colors the hydrogen. If you use the brown hydrogen, it is made from the either coal and CO2 emitted to the atmosphere, then we call that is brown hydrogen. If you have produced hydrogen by using the natural gas, again CO2 emitted into atmosphere, then we call it that is the gray hydrogen. But we have again produced hydrogen by natural gas, but if you capture the CO2 emissions when you are producing the hydrogen and it is stored, then we call that is blue hydrogen. Then green hydrogen, this is the future hydrogen based hydrogen. If you make the hydrogen production using renewable electricity, and if there is no CO2 emissions during that process, then we call that is the green hydrogen. Okay, so yeah, so this is the future technology which we can going to use for hydrogen production most of the part. So we'll use renewable power which are coming from the cheap electricity, and use water to produce hydrogen, and again this produced hydrogen which will be used later for different um, applications. So 25 plus countries are planning for green hydrogen production, including India. Again, India is record low energy tariff with will give the driving force to generate the green hydrogen, because you have a very high and low cheap electricity which is coming from the renewables. So you want to encourage this production as well as the going with respect to renewable energy. Then obviously if you are not able to use in the grid, then you have to convert into other kind of fuels. That is like you can able to convert solar fuel like hydrogen from solar PV, using solar PV, which is producing electricity. That electricity we are going to use to produce hydrogen. So this will give the major driving force in terms of the green hydrogen production. You can see that India's green hydrogen, our goal is to have 1.5 mass per kg, can disturb the global energy and the chemical industry. That is the and maybe some big companies in India also have a goal to produce 1 kg of hydrogen to for $1. So that will give a major disruption in the global energy, the trade. So you can see 2030, the predictions of the hydrogen by different countries. So you can see that Japan will be like 2.5 USD per kg, and 2 US dollars per kg in European Union, other countries, and in India, some countries they can able to produce with $1.5 per kg of hydrogen. So if you are able to produce this 1.5 per kg, then you are going to have a net exporter, and the other countries which are going to have very high like cost of hydrogen production, they are going to be net importers. So by using this renewable energy and going to convert into hydrogen, and you can able to export to other countries, so that you can able to one side reduce the net imports of fossil fuel, and we are going to slowly start the exporting of hydrogen to other countries like Japan and other countries. So this will make like your import cost is going down, and also your exports will going to increase. This is the major important aspect of the green hydrogen mission in India. So what are the options we have for hydrogen storage? We have seen the production and fuel cells, but what are the options for hydrogen storage? So we can store at maybe high pressure gas cylinders. You can also use for liquid hydrogen and metal hydrates. Next talk, I'm going to talk about the metal hydrates, and we also you can also store in liquid chemicals and porous materials, and also carbon nanomaterials and glass microspheres. Also, we can store the hydrogen. This is the like conventional methods. If you store the hydrogen by high pressure gas cylinders, liquid metals. So this I will going to show in the next slides, next session. Just here I want to show what I have done in HISO systems. So where we used the metal hydride system for hydrogen storage and supply of to low temperature fuel cell for automotive applications. Just I want to show here, we have developed the golf cart, converted this battery based golf cart to fuel cell based golf cart. You can see here. So this is the fuel cell, and this is your hydrogen storage cylinder. Here you can see the different components. The first one is hydrogen storage cylinder. Then second one is the compressor based compressed gas based storage system. Then we have a pressure reducer, because this compressor gas cylinder will give like 300 bar to 700 bar, so that you cannot able to directly supply to the fuel cell. So we have to reduce this pressure by using this pressure reducer. Then we have a hydrogen recharge valve to again recharge this both the cylinders. Then we have a heat exchanger for this container, and we have 6 to 10 that air liquid heat exchangers. 11th is your fuel cell stack. So initially, as I said, the fuel cell will generate electricity, but you may have some byproduct of heat, so that you have to remove efficiently to produce electricity efficiently. So that waste heat which are going to use to release the hydrogen from this container. Basically, this hydrogen supply from metal hydride will be endothermic reaction, so that you need heat to release the hydrogen. So that heat we are taking directly from the fuel cell, which is generating by producing the electricity. So we are able to use the waste heat which is coming from the fuel cell and able to give to the metal hydride container, so that it can produce hydrogen to supply to the fuel cell. So in this way, we are using the waste heat which is coming from fuel cell and driving the hydrogen desorption process. So here we tested with two different ways. One is initially we have tested only with metal hydride container, how much it can range, give the vehicle. Then we have tested almost 1 hour the driving range of the vehicle. Then in second case, what we have done is we have added some kind of this compressor gas cylinder, so that how much distance it can increase compared to that initial case. You can see that the range is increased to almost 2 hours, because this production, the hydrogen desorption is stopped at the metal hydride after 1 hour, so that the fuel cell cannot able to generate the electricity. Whereas here, because both the cylinders are dissolving the hydrogen to supply to the fuel cell, so that it can run up to 2 hours. The main because is because if you take the entire hydrogen from the metal hydride, so it is not able to dissolve the hydrogen, because it's endothermic reaction. It is maybe the temperature is going down. It means that your pressure also will come down. So the supply pressure of the storage tank is not a requirement to the fuel cell, so that you are not able to supply the hydrogen requirement of the fuel cell, so your fuel cell stopped. Whereas here, because we are taking from both the cylinders, then the supply from the metal hydride is very low compared to the compressed gas, so that your temperature and pressure requirement will be high compared to the fuel cell requirements, so that you can able to run the vehicle almost 2 hours here. Here you can see how these two cylinders supplied the hydrogen to the fuel cells tank. See, you can see that metal hydride usage and also compressor gas hydrogen usage. So combinedly, you are adding you see the pressure requirement. See, is coming down by the number of hours. So initially, the number of the pressure inside the compressor tank is low, high, so that when you are removing that hydrogen, so the pressure will come down within the cylinder. Here you can see the flow rate requirement of the fuel cell with respect to almost 300 minutes by using the both the cylinders. And also here you can see the utilization of hydrogen from various the two cylinders with respect to the time. Here just I want to show, see, initially we have means the hydrogen is coming from compressor gas, because the fuel cell is just started, it will not give enough waste heat, so which will drive the metal hydride. So initially we are going to get this is going to use the compressor gas cylinder. Then the later, once you are getting the waste heat which is going to supply to the fuel metal hydride, so this metal hydride will supply the remaining hydrogen, so that you can able to use the both the cylinders to increase your uh, range of the vehicle. And also we have developed this hydrogen based compressor. So because, as I said, if you going to use the compressor based hydrogen storage, then you have to at least compress either 350 bar or 700 bar, like type 3 hydrogen storage cylinders, the composite cylinders, which can hold up to 350 bar, whereas type 4 you are going to increase to like 700 bar or 750 bar, then we should use the mechanical compressors to compress the hydrogen. But as you know, the mechanical compressor use the electricity, which is high grade energy again. So we have developed here the three-stage hydrogen compressor, where we are able to use the waste heat which is coming from industry, so that will drive the compressor. You can see here we have compressed hydrogen by using low grade steam, 120 140 degrees centigrade, and cooling water 50 to 25 degrees. uh, this is available at industrial customers, so that you don't need to use the electricity which is high grade energy to compress hydrogen. Okay, so this technology we have handed to that company, so which are funded for this project. So in this hydrogen compressor, we have used three different kinds of alloys to compress hydrogen from like a different pressures. Like suppose if you in that inlet pressure of your compressor is 3 bar, then in first stage we are compressing 20 bar, then again from 20 bar to 50 bar, second stage compression, and 50 to 200 bar in third stage compression, so that you are finally you are able to compress from 3 bar to 20 bar by using different kind of alloys which can absorb dissolve the hydrogen at different temperatures and pressures. So you can see the cyclics of hydrogen compression, how we are achieving the compression at different cycles. These are different storage applications used previously by using the metal hydrides. So this is automotive buses using the fuel cells. And uh, I want to show just another project which we have done with AICTE Japan. So there again, as I said, you are able to get renewable energy and supply. It's again intermittent nature. Like solar, you will get daytime, and the wind also you have fluctuations. Suppose your demand and supply is not matching, then in that case you need to have a energy storage system. But you can use batteries for small scale, but if you want to use the energy storage system for the large scale, then batteries, the cost is very high for storing. In that case we can use the electrolyzer and fuel cell and hydrogen storage tank, so that we can able to convert the excess supply from the grid. When you don't have demand, then that electricity you can able to use the electricity electrolyzer, that is converted into hydrogen and you will store. And maybe during peak hours, when you don't have supply from the grid and your demand is very high, you can convert the stored hydrogen by using the fuel cell, which will be able to electricity, so that you can match the supply and demand by using this kind of energy storage system. Uh, and other aspect is, suppose if you want to use this hydrogen for your hydrogen vehicles, then you can supply this hydrogen stored to refilling stations, then that refilling stations which refill the vehicles. So you can basically you can tackle the grid problem, as well as you can tackle the hydrogen fuel for the transport sector. uh, so by using this kind of system, we can able to store the renewable energy, intermittent nature, and supply your electric power, hydrogen, and thermal energy. So this is what we have developed. That is unitized reversible fuel cell, means it can work as electrolyzer and fuel cell depend upon the mode of operation. You can also see the what we have developed. This is metal hydro storage tank to store the hydrogen and release, absorb and dissolve by various process of URFC. You can see that the inner parts of your URFC, you have a stack here, and you have a DC load for testing the equipment, and DC power. When you are giving the in electrolyzer mode, you have to give the supply to the electrolyzer so that it will generate the hydrogen. And DC load, when you are operating in fuel cell mode, you have to apply some load to because it will generate the electricity, so that has to be taken by some DC load, which is we are tested here. So in this UFC, we have 10 cells, and each cell having cross-section area of 250 centimeter square. So in electrolyzer mode, this the power capacity is 4.4 kilowatt, and in fuel cell mode, it can generate up to 680 watt. So here we have used a metal hydro storage tank as a hydrogen storage, because this is stationary applications to store the renewable energy, and again to produce electricity whenever we need. This is the principle of unitized reversible fuel cell. So it can work as electrolyzer mode, and you can reverse it, and you can work as a fuel cell mode. So the cathode will become anode in fuel cell, whereas anode in electrolyzer mode will become cathode. So these are the different parts of the fuel cell and different materials what we have used here. So as I said, membrane, most of the fuel cells we use Nafion membranes. Here we use Nafion 115, and the catalyst platinum, and oxygen side it's a platinum plus uranium. So as I said, this the cost of the platinum is very high. So the some research is going on to reduce this platinum content in the catalyst layer. And the gas diffusion layer, from hydrogen side it's a carbon paper, whereas in oxygen side titanium felt. And again in bipolar plate, this is the most thickest part of the fuel cell part, that is used by the titanium. And again active area of fuel cell is 250 centimeter square, number of cells is again 10. You can see the various the parts of the system, because in fuel cell or electrolyzer the stack is small, but you have other components that is required for a balance of plant, that is very very important in terms of engineering aspects. So apart from the stack, you should also design the system, the balance of plant, various component, such a way that you are going to get very high efficiency in terms of system level. Because people say that stack is 80% or 60% efficiency, but if you don't design your balance of plant with high efficiency, your system efficiency, total system efficiency can come down to 40 to 50%. This is because of low efficiency of or maybe weak design, or low efficiency design of your balance plant. So this ERFC can work as electrolyzer mode as well as the fuel cell mode, which will be used in single unit. Why we use single unit? Because uh, either you need to supply electricity, or you need to supply electrolyzer electricity from the grid. So either one mode you are going to use. So instead of two systems, if you make a single system, so that your capital cost going to reduce maybe 60% or 50%. So the red side, the hydrogen is going to take place, and this side either oxygen or air, and by using some water vapor also we can able to collect from this side. So as I said, it can work both electrolyzer mode and fuel cell mode of operation, and it can bring down the capital cost compared to individual systems, because if you use electrolyzer different component and fuel cell different component, but you will use it in at a time only one operation. So other systems should be in idle case. High operating ratio per one device, because most of the time you will use either in electrolyzer mode and fuel cell mode, and because in one system you are using, it should have very less maintenance parts. In hydrogen storage, again we have three technologies: compressed form, liquid form, and solid form. So in this case, we have used the metal hydride storage because it's a stationary applications. So this is the schematic of storage metal hydride storage tank which we have designed and fabricated. Here you can see we have used double coil heat exchanger because, as I said, metal hydrides, it's a like absorption desorption. Then you need to supply heat and you have to remove the heat in during absorption and desorption. So this is how we tested the system during the sunny day. Like you are getting electricity from solar PV, so that solar PV will increase during daytime up to the noon. Then again it will decrease the power from the solar PV plant. So just similar to that, we have given power to the electrolyzer. It will increase and it is going to decrease. And just we want to see how it is tackling the change in power, input power to the electrolyzer. Here you can see how it is produced hydrogen by taking this power which is coming from the solar PV plant. Okay, so it is same as the curve is same pattern similar to your power supply, so that the hydrogen supply flow rate also, production rate also will directly proportional to your power requirement of the electrolyzer. Then during 10 hours we have generated hydrogen. Then later, because you will not get any power from the solar PV, then you have to generate the electricity through fuel cells. Again we supplied the hydrogen to the fuel cell mode. Okay, then the power generated from the fuel cell with this from the same system. So this is during a night time and this is your daytime. So power is supplied to the electrolyzer, produce hydrogen. The same hydrogen we use nighttime to produce again electricity. This is kind of your renewable energy storage system. This is again result for the MH storage tank. Some performance parameters. This is how we will see the energy flow in terms of input to the electrolyzer and storage and the output converting again from fuel cell. Okay, so how this is how energy flows from power input to electrolysis part and storage part again in fuel cell mode. Okay, again we tested for a cloud area test. Yeah, so these are the similar applications we can see in German. I think this is in airport. So there people are using wind turbines and converting hydrogen again supplying to hydrogen differentiation storage again CH applications to convert back to electricity. This is also similar way what we have tested in Japan. So this is the future scope of the energy system. You'll use both electricity for transport, hydrogen, and the environment is very clean because you will not produce it any CO2 emissions. Okay. Same thing with solar PV, and also you can see the another example how hydrogen-based energy storage system is working in hydrogen island in Norway. So there also people are using the wind energy, the excess power again converted into hydrogen. Then they are going to use the grid stabilization equipment to the grid of this the Utsira island in Norway. Some examples of hydrogen vehicles. Okay. Yeah, so the challenges. Yeah, thank you.
Thank you, Dr. Satya, for giving the insight, various insight in this hydrogen energy storage technology. Now that question and answer, if you have any question, I request all the participants, if you have any questions, please. Please, sir, please, you
Hello.
can ask question. Yeah, one by one.
Y- Yeah, hi. Good evening. Good evening, Professor. I just
Good
wanted
evening,
to
sir.
know one thing. It's
Yeah.
like just now in the recent slide you shown that the energy conversion from hydrogen to electricity, then electricity to hydrogen.
Yes, sir.
What are the loss factor over there? I mean, if we convert electricity 1 kilowatt, we are using for
Mm.
like 1 kg of hydrogen, and then
Mm.
we will convert it to the electricity again, then how much kilowatt we will have? Like, as I know, 50, 60 kilowatt is usually used to create a 1 kg of hydrogen in normal form. And then when we will use the hydrogen to convert again in electricity, what would be the loss factor over there?
Yeah, it's a good question, sir. Uh, if you see, the electrolyzer efficiency is very high compared to fuel cell. Suppose you are
Hmm.
going to convert 80 to 85% of conversion with electrolyzer from electricity to hydrogen. Again,
Okay,
from hydrogen, you are able to convert into using fuel cell. That is giving around 50 to 60%. So if you combine both 60% and 80%, then you will get around 45 to 50% conversion rate
okay,
from power to
okay.
power. But
Uh,
this is like you cannot compete with battery. But again, the battery problem is that the large scale system. Large scale
okay,
system,
okay.
the cost is very high. But this, you suppose you see that why this, even though 40%, 50% is important. Suppose you are getting the daytime cost of electricity is 2.2 rupees or 2.5 rupees, but
Hmm.
at the end, you can, in the night time, you can able to generate maybe 3 rupees or 3.5 rupees. But now you are paying almost 7 rupees to 12 rupees in different cities in India. So in
Right,
each
right,
time you can
certainly.
able to generate with 3.5 rupees or 4 rupees of electricity. That is still cheap compared to the other forms of energy.
Correct, correct. That's what I was wondering because the only thing is that if the loss factor is quite low and efficiency would be high for the conversion in both the end, in both the way, so it will reduce the cost a lot, I believe, and we can easily implement it for the large scale solar park and other places as well.
Yeah, so I think you may heard about the DST is going to have three hydrogen valleys in India. So they are going to
Mhm.
have a similar concept of hydrogen production and storage and utilization. Yeah,
Okay.
you're right. Yes.
Thank you. Thank you so much. It was
Yeah.
a really informative session for us. Thanks.
Yeah. Thank you.
Hello,
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 hello.
hello, sir.
Sir, this is Dr. Prabhakaran from Mohan Babu University, Tirupati, sir.
Yeah, please,
Hello.
sir. Please.
Sir, in place of metal hydride, can we use the LOHC, sir? Liquid organic.
Yes, sir. So yeah, see, we can use different applications, different storage methods. But here we have used stationary application using the metal hydride, which can. And one more thing, in Japan there is a pressure limits, so we should not go beyond 10 bar. So that's why you use the metal hydride for low pressure applications.
Okay, sir. Sir, what
Yeah,
about
we will have a different applications, like some people convert into ammonia, so that will be easy to transport to other places. Uh, like we have different technologies available, but still we like no particular technology is best suited for best applications. Still R&D is going on.
so based on the application, we can choose the LOHC or metal hydride.
Yeah.
Am I right,
Yes.
sir?
Yes. Yes. Yeah.
So what is the advantage of using LOHC, sir, compared to metal hydride?
The cost of storage will be cheap compared to metal hydride.
Oh, thank you, sir. Recently, I gone through the LOHC storage system.
Yeah. Yeah. Yes.
So
Okay.
that's what I'm asking, sir. Whether we can adopt this technology, LOHC technology for waste heat recovery also, sir. By after fuel cell, we are getting some heat, no, sir, 100 degrees centigrade.
Yeah. Yeah. Yeah.
So that heat can be used to preheat the LOHC for in terms of gas state, sir.
Yeah, I think similar way we are using the metal hydride because metal hydride hydrogen desorption is endothermic. So we are supplying from fuel cell waste heat to release the hydrogen again from metal hydride. Yeah, same thing, same concept. Maybe you can use.
Can I use this method to implement in the IC engine, sir?
IC engines having some technical problems related to hydrogen, but still R&D is going on because of backfiring and all. Yeah.
Okay, sir. Thank you, sir. Thank you, sir.
Hello, sir.
Hello, sir.
Yes, sir. Yes, sir.
Hello, sir.
Yes,
I
sir.
have
Please.
one question.
Yeah.
Yes, sir. Sir, in IC engine, if we use some multiple fuels like hydrogen, biodiesel, and alcoholic fuel, so for such combination, can we use EGR?
I'm not expert in ICE engine based hydrogen, but people are using this multi-fuel engines. Yeah.
So for such combination, can we use EGR, sir? Exhaust gas recirculation.
Sir, we can
I
use, sir.
think
We can use.
I think it will create a problem because hydrogen combustion, it will again spark. It will ignite with if you have very high temperature.
If we use the cold EGR, then will it be uh, problematic,
Yeah,
sir?
but that's what I'm not expert in hydrogen ICE engine based hydrogen. Yes.
Oh,
Sir, recently I
okay,
published
sir.
one paper in the International Journal of Hydrogen Energy, sir. We can use that EGR technology for IC engines, sir.
Okay. 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 Yeah.
Sir, either cold EGR or hot EGR.
Sir, hot EGR, sir.
We can use hot EGR.
Yes, sir. Yes, sir.
So there will not be any problem in
NOx
induction.
emissions. Sir, yeah, maximum reduction
Yes,
is
yes,
possible, sir. NOx can be
yes,
reduced
yes.
by
Okay.
using this EGR system, sir. You can adopt SCR technology
Uh,
also, sir.
but I have some doubts, sir. If we supply the EGR to
Yeah, sir.
again intake manifold, so if there is any problem,
Sir, Yusuf, sir, can I join after again 5-10 minutes for second session?
No, no problem, no problem. So we take your break for 5 to 10 minutes.
Yes, sir.
So let me. I want to address the participants. There are
Okay.
some couple of participants raising the questions.
Yeah,
After 10 minutes,
we can take
after
again
10
after
minutes,
this my session. Yes, sir.
Satya will
Yeah.
answer the question.
Okay, sir.
No
Okay.
problem, no problem.
Okay.
Thank you.
Okay, sir. I will join in
Take a
5-10
break
minutes.
now.
Yes.
Yeah.
Okay, sir. Yeah.
So yeah. So dear participants, so I like to convey the things here. The Saturday, as per the schedule, the international speaker will join at 2 o'clock. Then that examination related things we like to keep it before the after the valedictory. There will be the interchange in the program. So once valedictory over, so that guest will be going for what you call that, and they move out. Then after that we can have an online examinations. It is on a basic level of this green hydrogens, whatever the things which is shared by your expert and whatever you learn from here, it is a basic level questions only. It is an objective type. Please, you can basic level. It's you can learn as a teacher, as a PhD scholar, and so remaining back end, we will support you. But you taken a time. Can we get PPT? So PPT will be shared. Some of them will be. So yesterday's session where the nominees are about to join by tomorrow. So the session will be in tomorrow. I think this afternoon. Sorry, the first session. Once his session is over, he will share. So we will circulate once that the speakers is given this PPT. We will circulate to all the participants without any hesitations. But your active participation is really gives a support to the speakers and encouragement to the speakers to who deliver the knowledge to share with you. So it is a good informative. So any some specific questions I like to address. Some of them we have some limitation. I beginning itself told that there was in the yesterday meeting it was in more than 2 GB it seems. So the sharing also it is in majority of the participants is having some apart from the Gmail account. There are other mail accounts. So means it's not possible to share with them. So we will try to give it in what you call it on a different mode. And we'll find out the technical possibilities. If you have any other specific questions, so please I like to answer it. So over to the participants.
Hello.
Yes, sir. Yes, sir. Ankur Sachidev, sir. Please, sir.
Yes, sir. Sir, my question. Good evening, sir.
Good evening, Professor.
Okay. Sir, my question is: does using hydrogen as a fuel does not lead to emissions in the atmosphere? Because I read somewhere that water vapor higher in the altitude disturb the balance between the ozone and the CO2.
Uh,
So, are we trading one problem with the another? Is that the case?
no, there was some disturbance. Could you repeat your question? So let me find out the answer for that.
So,
Hello?
my question is: does water vapor also leads to global warming in the atmosphere?
Okay, the global warming which is happening because of the greenhouse gas emission, that is
Yes,
main
sir.
causes. So the greenhouse gas
Okay.
emission, when you are combust this what you call the hydrocarbon fuel, all the hydrocarbon fuel what you call the in the fossil fuel it is called, or what you call it in your petrol, diesel, natural gas. So we are using this kind of energy sources of energy for our day-to-day activities. These are the things which is main causes for this global warming. That's what that universal goal where the sustainable development goal. There was in COP 29 conference 26 earlier they decided the government of India like to have what you call it in this global market. We are going to reduce to 2070. What do you call it? And we are in a carbon-free country. So based on that statement, they made it what you call it a green hydrogen project, the green hydrogen mission. So this was is happening. So it takes some time to materialize or take the infrastructure development in a better way. So government also spending more than 2 lakh crores investing on this new. It is a new generation energy systems. So sometimes Satya used to organize what do you call it, student course on this next generation of fuels. So where this transition is going to be happen. So definitely this emission none of things will be come down, no issues.
Okay, sir. Because water vapor is also a greenhouse gas, sir.
Water vapor, you say it is a greenhouse gas. What is the
Yes, sir.
constituent of this water vapor? It consists of H2O or any other gases which is happening inside.
No, sir. H2O only, but I studied somewhere that higher in the altitude, it disturbs the balance between CO2 ozone also. And
Take
these
it.
two, that this is the point I want to say.
Okay, okay. Thank you. Thanks for sharing the message. So one more information I will share this what you call that some research articles. I think participants supposed to be submit. I think how many of them is so attending this course online FTP is a first time. Probably you might be aware of that. We are also adding your attendance in your login ID. So after 2 days, you can check your attendance based on the Google Sheet, which is generated to us. That is an evidence. And moreover, what you call that and feedback, which is also you are submitting through online. We are checking both the things, and we are giving an what you call that an attendance. We are uploading attendance in your portal. So some of them is not getting it out. Others, some people are. We already uploaded day one attendance. Please, you can check it out. Tomorrow afternoon, we will add all day one and day two attendance from my side. And regarding this research article, so the template we like to share. So on the last day, so whatever the things you learn from this all yesterday and today and going to be learned for next 4 days. So you can give an summarized way. So it is in one page report. So it will be it is needed for an AICTE. Once what you call it you submit your feedback and the attendance is completed. So probably you will get a certificate on the next day from the ATAL portal itself. So that is the procedure which is happening. Modality is happening over there.
Okay, sir. I want to know one more thing, that we have
Yes,
to
ma'am.
submit the report day by day or on the
No,
last
no, no,
session?
on the last day, madam. Last day. That's what I said. What you call it? Then we are keeping your online examination after the valedictory.
Okay.
Anything is
Thank
there,
you.
you can discuss. We will be online. Me and my coordinator will be online, so we can discuss.
Okay. Thank you.
Okay, ma'am. I think Dr. Satya is joined. Dr. Satya, sir, you joined back.
Yes, sir. Am I audible now?
Yes, yes. So I once again I welcome all my participants and the speakers for the session 4. So already we introduced our Satya. So now I like to I'm handing over the session to Dr. Satya. Satya, please.
Yeah, thank you, sir. Yeah, so in previous session, I have taken more emphasis on integrated hydrogen energy systems. So in this session, I will more talk about the metal hydride-based hydrogen systems and the various applications of metal hydrides.
Excuse me, Dr. Satya, there are two participants. They raised the questions in the last session closing.
Okay.
One, Mr. Pasil and Dr. Turjo Tarvi.
Okay,
So,
sir. We can take up. No problem.
okay, thank you.
Sir, could you explain the future research areas in green hydrogen?
I think I have. I said in fuel cell system development. See, we need metals people, we need chemical people, we need mechanical people, and we need electrical people. Without these four, you cannot get fuel cell total system integration with respect to renewable energy, or integration in the fuel cell, maybe buses, because it is a multidisciplinary area. People work in different areas. I think I have shown, maybe just I'll show. Yeah, these are the challenges currently we are facing in hydrogen economy, like production. Yes, we are getting good efficiency, but how to reduce the cost of hydrogen production cost. Now we are getting around $4 to $5, but our goal is to go for one to $2 by 2030, because that will give major advantage to export the hydrogen. Then the second is storage. Yeah, storage is having a lot of issues related to kinds of different storage, like compressed hydrogen storage. We need to have a technology related to composite cylinders, which is again mechanical and chemical research area. Then distribution, again, you have problem with the pipelines, because hydrogen enrichment is also major impact. Like you have to make some kind of pipelines which will not have hydrogen enrichment in long term applications. Again, utilization side, the fuel cell cost has to come down, because many like technology has to improve to, so that we can decrease the cost of production of fuel cell, as well as the maybe the individual component cost, and balance of plant has to improve, so that we can get major efficiency like improvement. So these are the different challenges related to hydrogen economy. Uh, Obviously there is a lot of scope in hydrogen energy, because this is upcoming technology. Currently we have batteries already there, but the hydrogen is going to be a big movement in India. DST also focusing on hydrogen in big ways. To they want to support different projects on hydrogen. So as I said, we are going to have uh, three different valleys which are funded by DST, like 50 crores each project, like for different institutes. I think this is going to come in the next 1 or 2 months from the DST. Yes,
Okay,
sir.
sir. Thank you. Thank you, sir.
Yes, sir. Is there another question?
Yes, sir. Good evening.
Yeah, good
Can
evening,
you?
sir.
Yeah. And which type of electrolyzer technology is the best for reducing the cost of hydrogen?
Obviously, we have two technologies which are going to have feature, like one is alkaline, then second is PEM electrolyzer.
Yes.
Yeah, so these two is going to have a future technologies which are we'll be using to for hydrogen production through renewable energy, through solar PV or wind energy.
Oh, I'm asking about what is the impact on the LCOH, the levelized cost of hydrogen? Maybe if we consider alkaline,
Yeah.
so maybe the electrolyzer manufacturers will give only the stack. The remaining, the BOP balance of the plant, we need to arrange. Maybe coming to the PEM electrolyzer, everything is inbuilt, like BOP and stack, everything is integrated. But coming to the cost wise, the both electrolyzers are is almost same, like a little bit cheaper. The alkaline is almost same. Maybe if we compare, then how come it is influencing the LCOH? Even if you look into the India, most of the people are concentrating on only alkaline only. And what is the reason for that?
Uh, PEM actually basically you need a very high, that purity of water should be very high, and the cost is currently the PEM is higher than the alkanic. And as I said, we are using in PEM electrolyzer the platinum is the catalyst. That is the cost driving component in the PEM electrolyzer. So once if you have different kinds of alloys which can able to replace some percentage of platinum in the electrodes, then the cost may come down. That's what now the last, like in batteries 10 years back, how the research turned into that the cost of batteries come down. Similar way it will happen in hydrogen also. By maybe 2030 or 2035, the cost will become at least half of the cost compared to at present. Maybe you go for PEM based electrolyzer, or you can go for alkanic based electrolyzer.
Okay, sir. Thank you.
Can I start, sir?
Yes, sir. Yes, please, sir. We can have remaining question after this session, sir.
Yes, sir. Yes, sure. Yeah. So in this session, I'm going to more concentrate about the metal hydride systems for various applications. So this I explained already. Now, as I said, we have a grid problem related to supply and demand because of you are going to increase. Currently, we have around 440, 450 gigawatt of total capacity in grid. So 450, you are going to increase again 400 gigawatt by renewable energy by 2030. It means that you are going to have 50% of renewable energy in the grid, more than 50% of renewable energy in the grid. So you understand that how this intermittent renewable energy sources will impact on the grid stability. That is very, very important. Sometimes you may heard about the grid failure in national grid. Then you may have entire power cut for the most of the states. So this also will create a major hurdle to manage the grid without having any failure. So that's what we need, some kind of storage technologies to store the excess energy and give back whenever your grid is having lot of demand. So just I'm showing we have different technologies, like we have batteries. Obviously, these are very good energy storage systems, but not for range. You can see the range. So these are small ranges, like up to 10 megawatt. We can able to use the battery technologies. And see, another one is the important is pumped hydro power storage. So this is mature technology, because people may know that the water dams, the hydraulic power plants. Basically, these we call that is pumped hydropower storage systems. In hydraulic dams, we used to have like a turbine which is going to take the energy from the water and convert into electricity. Now, because of the adding this renewable energy into the grid, so people are using the same technology for energy storage. So you have suppose excess supply from the renewables to the grid, then what you do is you just pump back this water from down to top, so that you are storing again energy in terms of water. So that water again you are able to use during maybe peak hours, or when you don't have a power from the renewable energy, so that you can able to use to down. This is very high mature technology, because the turbine is highly matured, and we can get at least 90% energy efficiency, like when you are using for a turbine or using in pumped mode. So both will get 90 to 85 to 85%, so that the round trip efficiency you will get 70%. So this is very good kind of storage for renewable energy. I think some states already started using this kind of energy storage, uh, and some the private companies also invested in this pumped hydropower storage system. So but the main problem is that you cannot implement in, start this new kind of sites, because starting getting this hydrogen dam, like hydropower plants dam and evacuation, it is having lengthy, like in India we used to have like 20-30 years to create one dam and produce the power, and the sites available also is limited and depend upon the season, and also it's having problem, like in summer you may not have water in the dam, so that will create problem for the storage. So even though this is very mature technology, but still this is having a lot of drawbacks related to number of sites availability, number of power plants availability. Then we have other technologies is upcoming, hydrogen, as I said, and we have a compressed air storage system also coming up, and we have another one is recent one is Carnot battery. So I'll explain about later what is Carnot battery here. So these can work for the large scale, like 100 megawatt to 1 gigawatt, because this is very very important in terms of grid management in the long range applications. If you see the storage technology maturity, as I said, in mechanical way, you can use the pumped storage hydro system. This is technology wise very mature, and the efficiency also is very high. Then electromechanical, you can use the compressed air energy storage and flywheel energy storage. These are still in commercial mode and deploy mode. Okay. Then demonstration stage compressed air storage in second generation, still it's going on. Then electrical, we have supercapacitor, magnetic energy storage, and other kind of energy storage systems. In electrical chemical, we have different batteries. Some are matured, some are in still advanced commercial deployment stage. Then chemical side, we have hydrogen storage, which is in currently in demonstration stage. Okay, so if you see the most storage technologies need mature, like only pumped and lead acid batteries are mature, but other technologies still in deployment stage or in demonstration stage or in R&D stage. So I think I have explained this. What are the available for options for hydrogen storage? We have major storage technologies. One is high pressure gas cylinders. Then is liquid hydrogen in cryogenic tanks. The third is solid state hydrogen storage and porous materials and carbon nanomaterials. I'll explain each one. If you come to that high pressure gas cylinders, as you know that hydrogen density is low, so you need to have a large volume to store the hydrogen. But if you compress the hydrogen, your density going to improve, so that you can store large amount of hydrogen within the small volume. Suppose currently we are using high pressure gas cylinders from 200 bar to 800 bar. So type 3 we can go up to 350 bar cylinders, composite cylinders. Then type 4 we can go up to 700 bar, 800 bar hydrogen you can able to store. Okay, so that is the major advantage. You can reduce the volume by compressing the hydrogen. But again, you have still the gravimetric density will be low compared to other technologies. Then you may have feel that unsafe because you are having a 700 bar storage cylinder in your car, that will give some psychological feeling that something is unsafe. But the major drawback of this storage is for compression. Obviously, you have to provide some energy. If you use mechanical compressor, then you have to use electrical energy to like you have to use compressor to compress from like 2 bar to 800 bar. So if you see the energy content requirement of compressing from 2 bar to 800 bar, then whatever you are compressing hydrogen, the 80% of content energy is required to compress from 200 to 800 bar. It means that at end of the compression, you have only 82% of energy. Remaining 18% already you have used to compress the hydrogen from low pressure to high pressure. So that is the major drawback in terms of energy requirement. But otherwise, it will give very good. The volume energy density is very high. Then the other method, we will use liquid hydrogen. See, liquid hydrogen, as you know, that hydrogen can be liquefied at a very low temperature. You have to go at up to 20 Kelvin for ambient pressure. So you with this you will get a very high density, like 70 kg per meter cube. But again, the drawback is boil off losses, because whatever you insulate, but still some heat transfer takes place. That heat transfer, because you are inside this tank is below 20 Kelvin, then because that will drive from 290 Kelvin to 300 Kelvin to 20 Kelvin, the temperature difference is very high. Even though whatever you insulate, some heat transfer takes place. Because of that, the temperature increases again, it will generate the gases. So that gases you cannot stop inside the tank, because it will build up the pressure. So you have to release the boil off losses, whatever the hydrogen is converted from liquid to gas. So this will give some losses in terms of operation, and also for long term, obviously, because the more boil off losses will be there, so you are losing the hydrogen in terms of leakage from the your tank. So this is not at all good for long term operation. And another problem is that to liquefy hydrogen, if you see the energy content, it is taking around 35% of energy. It means that if you liquefy 1 kg of hydrogen from gaseous state to liquid state, in that 350 grams of hydrogen in terms of energy is lost for liquefying. Sorry, only 65% of energy content is available. So this will be a major drawback for hydrogen storage system. You can also see the comparison of various storage medium for hydrogen, like I am showing the metal hydrates and liquid hydrogen and compressed hydrogen in terms of grams of hydrogen per liter volume. So if you use metal hydrates, you can store up to like 100 to 100 grams per unit volume, whereas liquid hydrogen can only store 71 grams of hydrogen, whereas compressed hydrogen at 5000 psi it is only 23 grams of hydrogen. Then also you can see the comparison between different technologies, like magnesium alloy. This is the tank for same kind of hydrogen storage. You can see that different sizes requirement. Lanthanum you need little bit bigger, and liquid hydrogen it's still bigger the drum you need for storage tank for the same car. And if you store 200 bar, then your storage tank will be very high. Okay, so this will give the requirement of hydrogen storage tank for the vehicles. But our requirement, like Department of Energy USA requirement is, you should have a hydrogen storage system which can have 5-8 percentage, and operating temperature should be minus 20-50 degrees centigrade only. So this means that you cannot use the liquid hydrogen in vehicle applications. This is not a good way of storage for liquid hydrogen as per the DOE of USA. Then other constraint is you should have refilling rate. It should have 0.5 kg, half kg in a minute. You have to refill. Means it has to refill within a minute, at least half kg hydrogen you have to refill. Then the delivery pressure should have the 2.5 bar from your hydrogen storage tank. That is the requirement, because it has to go to supply to the fuel cell to generate the hydrogen. So the fuel cell needs at least above atmospheric pressure, so that your delivery pressure should from the tank should be 2.5 or above. It is most useful for the fuel cell operation. So these are the requirements, but none of the storage technologies currently can match this all the requirements of the like capacity wise, operating temperature wise, refilling time, and delivery pressure. You can see that solid state hydrogen storage hydrogen, the in physics, physically bound hydrogen, you have different materials like carbon nanotubes and carbon structures and geolites, MOFs, metal frameworks. See, these are different storage capacity, weight percentage. This is 5% of the carbon nanotubes, 1.5 per surface area of 1000 meters square per gram, and geolites you can get 2.2 percentage, MOFs you will get 4.5 percentage. This is very good, and this is also very good. But the problem you can see here, the operating conditions in the onboard storage, you need 77 Kelvin. This is will not will not come into the DOE target, because there we need only -20. So, and your pressure requirement is 4200 bar. These are decent, but the pressure is the main problem. The temperature is the main problem, because the remarks, it is related to carbon nanotubes, low weight percent at ambient conditions, need of cryogenic temperature for high weight percentage. So this will not fit for the onboard hydrogen storage application. Again, geolite, same problem. You need to have very low temperature, okay, theoretically low weight percentage, and the need of cryogenic temperature for high weight percent of hydrogen storage. So this will not fit for the onboard or stationary applications. Then metal frameworks, again, it's you need cryogenic temperature to store the hydrogen. Then chemically bound hydrogen metal hydrates, if you see the magnesium Li, you can go up to 5.4 percentage, and other low temperature alloys, titanium or other based elements, you can go up to 1.6 to 1.8 percentage. So the important thing is the operating temperature. Magnesium you need 300 degrees centigrade. Again, this is very high temperature. Then it will not suitable for the onboard applications, but stationary you can able to use to store the hydrogen. This 30 degrees and 20 bar, this is well suited for onboard applications, but the problem is that low weight percentage. You should have very high volume, means weight. You need to have very high to store same kind of hydrogen. The complex hydrogen, again, hydrates, you have very high weight percentage storage capacity, but again the operating conditions like 320 degrees centigrade temperature you need, and poor kinetics, and also problem with cycle stability, like absorption, desorption, same weight percentage, and high desorption temperatures, and regeneration issues also will be there. So I think in my previous session I explained that how we are using metal hydrates. Basically, these are intermetallic compounds formed by alloying of different metals by ball milling or melting. So here the hydrogen absorption process is a exothermic process, means that you supply hydrogen to the metal hydrate, it will become metal intermetal compounds, it will become metal hydrate, it will release also heat. That's called as exothermic reaction. So your exothermic range is 15 to 75 kilojoules per mole. It depends upon the what kind of alloy you are using for the hydrogen absorption. Again, in desorption, you have, it is like endothermic. So if you want to dissolve hydrogen from the metal hydrates, you have to supply the heat. Okay, this heat you have to supply to the metal hydrate. Then only you are able to dissolve hydrogen from your metal hydrate intermetallic alloys. So basically, these two are like, we can call this is heat-driven mass transfer phenomena. So without heat, you cannot dissolve hydrogen. Without removing the heat, you cannot absorb hydrogen. So you can play this heat transfer, and you can make some kind of the desorption rate, absorption rate, you can control with respect to your heat transfer. So this is very good, the research problem related to the the hydrogen desorption absorption by playing the heat interaction with respect to tank to the fluid. So based on this, the exothermic reaction and endothermic reaction, we have a variety of applications of metal hydrates. Like you can use hydrogen storage, as explained previous session, and also compressor. Yeah, yes, this is a very good application of metal hydrates, so that you can able to compress hydrogen by using low grade energy without going for high grade energy. Then by taking these examples of heat, we can also build some kind of refrigerator, heat pump, and also a major application is thermal energy storage. You can able to store the heat whenever you need. And another application is we have a heat transformer. I will explain some of the applications in my session. Yeah, so as I said, absorption is exothermic and desorption is endothermic. So these chemical compounds form when hydrogen gas reacts with metallites and alloys. You can see these are the process in absorption process. See, first we have a physics option. The hydrogen molecule will stick to your metal. Then you have a chemistry option. It will become two atoms. Then it will penetrate into the surface of the metal, that we call as surface penetration. Then fourth, it will diffuse into the surface of the metal. Then fifth, you may have nucleation and growth, so that you will form at the end of the fifth process metal hydride. Then in desorption, it is again it's reverse. So you will have hydrogen decomposition. Then it is through diffusion. Then it is surface penetration. Again recombination of two molecule atoms. Then you have a desorption to gas phase, like this. So absorption process and desorption process is entirely opposite. So you have a metal, plus if you supply hydrogen, it will absorb, and it will become metal hydride, and also the byproduct is heat. In desorption process, if you want to dissolve hydrogen from metal hydride, then you supply heat to the metal hydride, then it will become you will dissolve hydrogen, and then only metal is inside. So hydrogen storage by metal hydrides can store hydrogen at room temperature and atmospheric pressure. This is very important point for stationary applications. High storage capacities and ability to store, absorb, and release large amount of hydrogen many times without getting any deterioration. That people are tested up to 10,000 cycles. Then absorption and release rates can be easily controlled by adjusting temperature and pressure. As I said, by using this the heat and mass transfer phenomena, you can control the absorption rates as well as desorption rate by adjusting your supply and pressure. The environment friendly utilizes low grade thermal inputs for desorption, compact, and consists of no moving parts for various applications. Then safety storage media, particularly for mobile applications, because even if you have a leak, because without heat it will not dissolve hydrogen from the metal hydride. So that the safety wise, it is also very good point by using metal hydrides. Can be effectively used more than 15,000 cycles without having any reduction in the storage capacity. So here you can see how the absorption takes place. Okay, you supply the hydrogen, then it will sit into your free spaces. Then at this point, it is going to sites of the metal hydride. Then it will absorb at constant pressure, and again after this the sites are filled, then your pressure inside the tank will increase. So this part you can able to use for storage of hydrogen for desorption and absorption. Again depend upon the pressure and temperature, so that you can play with respect to different pressures and different temperatures, so that you can absorb and desorb hydrogen at different pressures and temperatures. So based on this PCT diagram, pressure composition temperature diagrams, we can make different kinds of applications of metal hydrides, like hydrogen storage, compressor, refrigerator, heat pump, heat transformer, thermal storage, and fuel cell applications. So here you can see this, by using this formula, you can play with respect to pressure and enthalpy and temperature. So you can able to get different pressures. These are the metal hydride based energy conversion systems. Basically, these are environment friendly, utilize low grade energy like input and output, and compact in construction. There is no moving parts, only hydrogen absorption desorption will be there. There is no vibration free and noiseless operation. Offer a wide range of operating conditions depend upon your PCT characteristics, and no liquid circuit, so hence it can be operated in any orientation. Okay, and also absorption rate and desorption rate can be easily controlled by using heat transfer, controlled by varying supply pressure. Okay. So this, I think, yeah. So we have discussed about the hydrogen heating value of different fuels. Hydrogen having high calorific value compared to that other fuels like petrol or diesel. Now I'm going to talk about this metal hydride based thermal storage system. So maybe in solar PV you will get electricity as the output, but you have other renewable systems. Those are like solar thermal systems. There, suppose you want to generate the power during peak hours by using the solar thermal power plant, then you should have some kind of storage system which can store during daytime. Then again, the same energy storage we can use to generate electricity during peak hours. This is very good case. Like suppose in India, some states like Delhi or in European Union countries, they have different tariffs. Like daytime, the tariff is different, and peak hours or night is tariff is different. So in that case, the solar thermal application with storage is also a major advantage compared to solar PV plus battery, because the cost comparison, you can generate thermal energy during daytime by using solar thermal collectors. That energy you can able to store in the storage system. Again, that use storage system for generating power in the peak hours, that will give added advantage. Currently, the solar thermal based systems are costly compared to solar PV, but if you compare with energy storage, then I think it may give same kind of the rates in terms of both solar thermal as well as solar PV plus battery. So you want to store the energy in the different ways, like sensible heat we can store, and the latent heat, and also we can also use the reversible chemical storage systems to store the renewable energy. So benefits: increase system reliability, so that you can make the fluctuations, because solar energy is intermittent. Suppose if you able to store some energy, if you have some clouds, then you can use the stored energy to produce electricity, so that your electricity production, you can be constant or depend upon your demand, you can match. So that is the major advantage if you use kind of some storage systems in the solar thermal power plants. So that will give to reduce the peaks of energy generation, because it will give the system reliability to generate the power related to your grid demand. Increase generation capacity. Obviously, the excess generation available during low demand periods can be stored in the storage tank. Again, we can increase the energy generation during the peak hours. That will give the great flexibility in terms of to the grid as well as the power plant. Reduction of costs of generation. As I said, by using seasonal demands, like in summer you may have a lot of solar power, and maybe in rainy season you may not have very high solar energy. So in that case, you can able to store, if you are able to store the energy in the during summer time, May, June, then if you are able to produce the stored energy using the during rainy season, when you don't have a good solar power, so that will give the reduction of costs in power generation. So we have different technologies in terms of thermal storage media. I think many people knows that the sensible heat storage in terms of liquid and solid, like we have a liquid, very matured storage media, that is molten salt. Currently, we are using solar thermal power plants, and some people still use concrete or cast steel for very high temperatures, like 1000 degrees centigrade, if you want to store the energy. But the cost, that volume of energy storage will be very high, and also cost also very high. The other people will be using that latent heat storage phase change materials by using hydrated salts and paraffins, but still this cost of energy storage also a little bit high. And cycle stability, we have to see how many cycles we can get with very good storage capacity. The recent one is thermochemical heat storage. This is getting very good focus on recent research, because you are able to store at very high temperatures. These are, again, we have a different materials. I'm I'm focusing on metal hydrates, how we can use thermochemical storage to store the thermal energy at different temperatures. So if you see, the advantage of metal hydrates is the thermal storage, high energy density than other thermal storage, means that 1 kg of material or one unit volume, if you compare with other storage materials, we can able to store very high energy density compared to that so maybe sensible heat or latent heat. That is the very good means important aspect of metal hydrides as a thermal storage system. Adapted to process like heat pumps for refrigeration, thermal upgradation, and also like it does not require any special purpose, and also they are very friendly to the environment because we are not getting any byproduct of like other harmful gases. So this is where we tested this metal hydride based heat storage device by using like magnesium alloy, magnesium plus 30% of MnF5 and other material. So where we have stored the heat with 714 kilojoules per kg of material we used. So the energy storage efficiency is 0.743, means that it is around 70% of efficiency we are going to get by using this kind of material, and excess efficiency is almost it is around 60%. Here you can see how we are tested with respect to different pressures, how much heat it stored with respect to using this kind of alloy. So you supply at 30 bar, okay, so then it will release the heat, so that if you are able to remove that heat by using kind of fluid, so then you can count that what is the inlet temperature and what is the outlet temperature of the reactor and what is the mass flow rate. If you calculate with respect to MCP delta T, then you can calculate how much amount of heat is stored by using this reactor. Again, this is again you can supply the same hydrogen to the reactor, then you will get back the same amount of heat. So that is the added advantage of using this kind of alloys. Then another application of metal hydrides is the heat pump application. As I said, suppose some industries will have a waste heat at 120 degrees centigrade or 100 degrees centigrade. Then how to use this waste heat? So by using this metal hydride, you can able to drive the system at low temperature, maybe at 120 or 140. Then you can able to get very low temperature heat output. But this can be used for your refrigeration or air conditioning application. See, here we are using the PCT of two metal hydrides. Suppose you have a metal hydride 1 and you have a metal hydride 2. So these two having two PCT characteristics, like it means that at same temperature these pressures are different. So by using these two pressures, we can play and we can construct a heat pump. Suppose one alloy you are supplying heat so that it will dissolve hydrogen. Thus, the dissolved hydrogen is going to get by another alloy, which will release heat at maybe 40 to 50 degrees centigrade. Once it is this desorption and absorption process is over, then you are decreasing the sensible heat, the temperatures. Okay, you cool it both the reactors. Then at this temperature at 40 degrees centigrade, okay, this pressure is less compared to this one. So here your temperature is maybe at 10 degrees or 5 degrees. You are supplying heat, maybe it is taken directly from the water. Suppose you are supplying water at 10 degrees centigrade, because it's endothermal reaction, so the water output may go 60 degrees or 5 degrees or 7 degrees. So that hydrogen is produced from this reactor, again it is absorbing the another reactor. It means that you are getting the cooling effect at 9 to or 8 to 10 degrees here. So this alloy will absorb heat at medium temperature like 35 to 45 degrees. So this will release to atmosphere. So by using again you can sensible heating up both the reactors to this temperature and this temperature. Again your cycle will continue. You supply heat at this temperature, it will dissolve hydrogen and same hydrogen will be absorbed here. So by in this way the cycle will continue, so that you are giving heat input at maybe 120 degrees centigrade or 100 degrees centigrade. You are getting cooling output at 9 to 10 degrees centigrade. This is one of the good applications for the metal hydrides. So in this way, we can generate cooling effect by giving heat input at 120 or 140 degrees centigrade. So you can see I am giving one schematic of one reactor. So this is your filter. Inside you have a metal hydride alloys. So you supply hydrogen from here, and it will go to the filter, and it is going to inside the absorb and dissolve hydrogen. Outside, you may pass some heat transfer fluid for absorption and desorption. Both cases, you can use this as a cooling media or heating media. So here, why using filter is because the metal hydride particles will be very, means size is very low. So when he is dissolving hydrogen, some particles will come along with hydrogen. To stop this hydrogen desorption, by using this filter, you can able to stop the metal hydride which is going along with the hydrogen, so that the metal hydride always will be there inside the reactor. That is the advantage of using a metal hydride porous tube as a filter. The other application is like, as I said, this is the you can use solar energy to drive this heat pump. Suppose you can supply, if you use a parabolic trough collector, I think many people knows that we can generate the heat by using parabolic trough collector from like medium temperature to high temperature, like 400 to 450 degrees centigrade. So that can use driving source to the heat pump, so that you are supplying heat at 150 to 170. So you are removing dissolving hydrogen to the low temperature one. It will absorb heat and it will release heat at maybe ambient conditions like 40 degrees or 50 degrees. Then in cooling mode, this will means again this will become again dissolve hydrogen by taking heat at low temperature. Again, that will be absorbed in the medium temperature. So again, you will superheat, then sensibly heat, then it will go to the original case. So this will go cyclic way, so that you are giving input at high temperature 150 170, and you are getting low heat maybe minus 15 or 0 degrees, depend upon your alloy. So you have to make a tailor-made alloys. By using two alloys, you can able to make one heat pump based on this metal hydride and hydrogen technology. Either you can use solar energy, or you can also use waste heat from the industry. So this is one application of metal hydride technology. Then another one is the metal hydride based heat transformer. So same concept you can use, but here what we are giving is, suppose you have a industrial waste heat at 80 degrees or 90 degrees, but you want heat in other process, you need a 200 degrees centigrade or 300 degrees centigrade. So using the same technology, you give heat at two different sources at medium temperature, and you can get a very high temperature at the outlet of one reactor. Okay, so by using the tailor-made, depend upon your operating temperatures and pressures, you can able to make the device to increase the temperature of the waste heat, or you can able to get the cooling effect. So this is one of the application of metal hydrides, which can run with input temperature 120, and you can upgrade the waste heat to 160 to 200. By using single stage, you can go up to 160, and if you use double state heat transformer, you can go up to 220. But what is the penalty? Penalty is, here we are supplying two places of heat, and we are getting one place of heat at high temperature. It means that the COP, obviously it will be less than 0.5, or efficiency you can call that is below 50%. But the advantage is you are able to use the waste heat which is coming from the industry. Then you are upgrading the waste heat to high temperature, which can be used for further applications like chemical industries or paper industries and all. So this is the external setup for both single stage and double state heat transformer. Yeah. So here you can see the thermodynamic properties and main applications. As I said, we have a different engineering applications of metal hydrides, but how to choose these alloys based on the properties. So that here you can see that for heat pumps, the selection criteria should be like high heat effects. The enthalpy change should be more than 40 kilojoules per mole, and you have a moderate pressures like absorption desorption should be like and entropy should be less than 1 ton joules per mole per Kelvin. So this is the criteria for selecting a metal hydride alloys for heat pump applications. Then you have another one which is used for heat storage. We need very high heat effects, at least 30 kilojoules per mole, and not too low H2 pressures for hydrogen absorption, it should be highly exothermic, so that your entropy should be have more than 110 joules per mole Kelvin. So this kind of alloys we can able to use for heat storage application. You can see that magnesium and other titanium alloys. The other application is compression. As I said, instead of using mechanical compressor, you can also use metal hydride compressor, which can compress hydrogen by taking waste heat or low temperature grade heat. So in this case, you have to choose your metal hydride. The heat range delta H should be 40 to 50, 20 to 40 kilojoules per mole, and it should compromise between energy input and compression ratio, the selection of metal hydrides. And also you should have the hydrogen desorption should be very high pressure at maybe 80 degrees to 120 degrees centigrade. So in such a case, that your entropy should have more than 90 joules per mole per Kelvin. Then another zone we have, that is hydrogen storage zone, where we need low energy consumption, because in hydrogen storage application, you should have give less heat input, so that it's easily dissolve hydrogen for fuel cell applications. Okay, so in this case, you have to choose the metal hydride alloy from this range. Okay, so the metal hydride storage safe and easy operation, and you should have a high H2 volume density, and you should get low quality of consumed energy, and for different applications like heat pump and compressor, you can use high temperature metal hydrides or low temperature metal hydrides. Okay. So promised NIC applications are like stationary and portable, hydrogen storage units for PEM fuel cell applications for backup power, and hydrogen storage and supply system for laboratories and special technology process, and special mobile applications, HT fuel, like forklifts and golf carts. You can able to use this kind of storage technologies. Here also you can see there is underwater autonomous vehicles. You can also use this kind of storage system, because there you don't have weight penalty, because you need some kind of weight to have the buoyancy in underwater vehicles. But the main is the poor dynamics because of heat transfer limitations, because the metal hydride thermal conductivity is very low. That is where you need engineering to improve the heat and mass transfer rates in terms of reactor design. As I said, the one of the application is the compressor. So here, by using different ways of the temperature inlet and outlet, you can able to control the pressures. Suppose you want to absorb the hydrogen, then in that case your metal hydride should have absorbed at low temperature. So once you are absorbed the hydrogen at low temperature, again you heated up the sensible heated up this reactor, suppose to 150 degrees centigrade. Means that because of this temperature change, the PCT, the pressure will increase, so that you will dissolve the hydrogen at very high pressure. Okay, so you are absorbing at low pressure hydrogen and you are dissolving at very high pressure. So if you make this kind of system in different stages, so that you can able to dissolve hydrogen at very high pressure, like 200 to 400 bar, by using the waste heat, which is from 150 degrees centigrade. It means that you are using low grade heat, and you are compressing hydrogen from low grade to very high, means low pressure to very high pressure, instead of mechanical compression. This is the one system people has designed, the metal hydride compressor using different alloys. This will be safe and easy operation, because mechanical compressor is moving parts are there. So suppose if some spark is generated during that movement, then because hydrogen is hydrogen needs very low energy requirement to fire, so that it will get easily fired up. So in this case there is no moving parts, so it's very easy and safe operation. Modular design, like good scalability, depend upon the number of stages and amount of alloy used. You can easy maintenance you can have. And another important is you can able to use the waste heat, which is 150 degrees centigrade. Like you can improve the hydrogen pressure from low pressure to high pressure. This will be very good, like integrated with some industries which is having very low heat as a waste heat. so that they can able to use their waste heat and compress hydrogen from low pressure to high pressure. But the main drawback is the low efficiency. But this low efficiency is not important. Suppose you have a waste heat or solar energy, which is we are not paying any amount that to that waste heat. Suppose just to without releasing to atmosphere, we are able to use that waste heat. Another important is slow dynamics and low productivity. This is also one of the issue related to metal hydride technology. Yeah. So you can able to use for laboratory facilities and space applications, hydrogen filling stations, okay, and like temperature sensors and actuators. This is how you manage the MS for heat management for various applications like refrigeration mode, heat application mode, and heat storage mode. Yeah. So as I said, there is a problem with that metal hydride based these thermal machines. One is that thermal management issues. As I said, this thermal conductivity is very low. So if you want to remove the waste heat from the during absorption process, it is not because your thermal conductivity is low. In that case, your heat transfer rate also low. Once if you are not able to remove that heat which is generated during absorption, then if your temperature of the metal hydride will increase, means your pressure also will increase. Means that your supply pressure is less than this metal hydride pressure, it will not absorb. It means that it will stop the absorption process. So if you are not able to remove the heat as much as possible fast rate, then your absorption kinetics will decrease. In same as in desorption, because in desorption you have to provide heat from outside to the metal hydride. It's the endosome reaction. If you are not able to supply heat as much as required, the heating rate, then it will dissolve. It will stop the desorption process, like we have seen in the previous session of the golf court. So you have to have you should have some kind of tailor-made things how to improve the thermal conductivity of the system, so that you can manage the heat transfer rate along with your hydrogen absorption and desorption. So here we have done some kind of thermal management heat transfer studies, how to increase this thermal conductivity, and we have tested and we have studied various temperatures and various pressures, how the hydrogen heat transfer rates are related. And also this is again with respect to compressor, mechanical compressors. You can see the difference comparison with the mechanical compressor range of efficiency, and this is the metal hydride compressor efficiency range. So if you want to improve the efficiency range, then obviously your cycle productivity also should increase. It means that again it will again is coming back to your heat transfer rate. So if you are able to increase the heat transfer rate, then you can able to increase the productivity, the compression rate, so that it will slightly matching with respect to your mechanical compressor efficiency. So these are the main factors influencing the hydrogen storage or discharge based on the storage capacity, thermodynamic and thermal properties, pressure and temperature conditions, reactor configuration, geometry. It is very important aspect in mechanical point of view, thermal design of overall storage device. This is also very good research topic. I think many people has done some novel designs how to overcome this low thermal conductivity. See some the heat transfer enhancement matrix I am showing here. Some people have used aluminum foam inside this reactor to improve the thermal conductivity of the metal hydride. Some are used like copper band they used, and some are used that aluminum band, and some are used copper fins to improve the thermal conductivity which is inside the reactor. And you can also see that combination of metal foams and fin in the reactor to improve the thermal conductivity which is inside the reactor, so that you can have the effective thermal conductivity we can improve, so that from 0.5 to like 2 or 3 or 4, so that your heat transfer rates also we can increase. Another method you can able to compress and add some kind of natural graphite, so that your thermal conductivity you can improve by compressing the metals, so that you will get very high thermal conductivity from 0.5 to 8 watts per meter Kelvin. so that your heat transfer rate will be increased, and you can also achieve very high good kinetics of absorption and desorption. So this is the model how we can study that hydrogen output or hydrogen absorption with respect to different kinds of flow rates of heat transfer fluid, and different heat transfer enhancement techniques we can able to use, by using this optimization of cooling tubes, heat supply rates, and temperatures we can play, and how we can see that different hydrogen supply rates and desorption rate we can manage. So these are the different reactors we made to increase the reaction kinetics and to improve that heat transfer effectiveness, and varying with respect to different temperatures and pressures. This is another kind of MH containment to improve the heat transfer rate, so that you have a large surface area to increase the heat transfer rate. Again, these are the different designs to improve the thermal management issues in hydrogen storage systems. This I think I explained the previous session. So where we are using the metal hydride storage tank here, this will be supplied to the fuel cell. So here again, in this case, we are also using the fins to improve the thermal conductivity of the metal hydride storage tank. So the conclusions from these studies, like heat transfer is a major factor directly controlling H2 absorption and desorption rate in metal hydride band, and influences the efficiency of conversion. Because if you want to increase the product rate, so that you should increase the heat transfer characteristics of the reactor is very important. And also you should have a special attention to the optimization of reactors, so that you are not only increasing the heat transfer rate, but you should not increase the storage capacity of the system, the CP, MCP. Maybe one side you can improve the heat transfer rate, but another side, if you are improving the CP, then still you need large amount of heat to supply when you need absorption and desorption phase. So you have to optimize both your improvement of heat transfer rate and the thermal capacity of the tank. That is the very important aspect when you are designing. So this is also one research area people can focus, how you can optimize the reactor size and with respect to the kinetics of hydrogen. Then people also use expanded natural graphite, how we can use improve the thermal conductivity within the system. And some people use the mitigation of this problem. They use the hybrid systems, both metal hydride system and compressor gas system. That's already we have seen in the Gulf cut, how we can reduce this impact of metal hydride at low thermal conductivity. Just we have a collaboration with National Sun at University of Taiwan, where we are studying with respect to PEM fuel cell and metal hydride storage system, how we can store the renewable energy by using the trigeneration plant. So as I said in the previous session, we have waste heat which is at 80 degrees that can able to use in organic Rankine cycle. Again, you can get some kind of electricity from the organic Rankine cycle. This will give additional power input, which is waste heat is coming from the PEM fuel cell. Again, the waste heat you can give to either vapor absorption system or vapor absorption system, so that again you can get the cooling effect byproduct which is coming from the waste heat by using PEM fuel cell. By using this trigen system, you can able to get electricity as well as heating and cooling. Basically we call it is combined heating and cooling and power system, CCHP system. Again, as I said, by using different technologies, we can also store thermal energy. So thermochemical is still in R&D stage, still molten salt and other in demonstration state. But this advantage of thermochemical is you can able to get a very high temperature heat output. I am showing another project we have with Japan, and we have the other international collaborators like KTH Sweden in the part of this project. This is international joint research project related to high temperature thermal storage technology. That is, we call that is Carnot battery. Suppose you have a renewable energy supply is more, then you convert this power into heat conversion by using either electrical heater or heat pump. Then you store this heat in terms of chemical heat pump or latent heat storage. Again, you are going back to power, heat to power conversion. So this is not efficient way, but still people use this kind of system for if you have very low power, very low cost of electricity which is coming down, and this can be integrated or retrofit with respect to current your coal-based thermal power plants, because the stored energy you are again using this the old power plant. So you are using same infrastructure for storing renewable energy, and again you are getting back power from the power plant. So this is another example of this Carnot battery. Discharge efficiency is again limited by Carnot efficiency in this case, and you are able to store the electricity. Here, just I'm showing the retrofit of your coal-based power plant. So you will get heat which is coming from the renewable energy, convert electricity to heat. Then you store either in latent heat form or thermochemical. Then use this waste that high temperature heat to drive your boiler, or using heat exchanger you generate water to steam. The same infrastructure you can able to utilize without throwing. So that round trip will be, you will get 40% efficiency. If your power conversion efficiency is more than 45%, then you will get 95% here. So you can able to get round trip is 40%, because people still use, because you have a lot of infrastructure is available, and if you are not able to use this coal-based power plant, this kind of system you can able to use the retrofitting to store the renewable energy. Just I am giving here one more example of how the Siemens renewable energy system is working with respect to this kind of Carnot battery, by taking the wind power and converting it to heat, and the same heat again they will generate electricity whenever you don't have much wind power. In this is one example in Germany. Again, the key technology for Carnot battery, it is like how efficiently you will store the energy. That is also important parameter when you are choosing the different kinds of materials. So you can see that other materials is like salt, which can store up to this energy densities 500, but you have a new materials which can able to store the energy density is very high, that is PCM based material, and thermochemical using hydrogen and titanium Li, you can able to get 10 megajoules per liter of the storage capacity. And you can see that the temperatures you can able to get around 600 to 700. So as you know, if you are a mechanical engineer, if your storage capacity temperature is very high, then your conversion efficiency also will be high. If you see the Carnot efficiency, your heat source temperature is high, then your conversion efficiency is high. So if you are able to have a very high temperature storage technology, then your conversion efficiency also will improve. Here we have two technologies which are working with respect to this international project. One is microencapsulated passenger material, which can store up to 600. Like here you can see that aluminum silicon alloy, which are they are used to have to store the heat in terms of phase change. The other one, what we are working is the thermochemical and storage, utilizing the reaction of reversible reaction with respect to titanium Li. This will give 120 kilojoules per 1 mole of hydrogen. But the important is the temperature. You can able to get 600 to 700 degrees centigrade, which is not possible currently with this salted heat storage media. So this is the advantage of the titanium. You can get very high storage density, 2600 kilojoules per kg, and at very high temperature. That is the important feature for this kind of storage media to store the renewable energy. Again, the same, you have absorption desorption, and you can play with respect to temperatures and piece pressures, so that you can able to utilize the stored energy like when you don't have much electricity from renewable sources. here either you can use the pressure difference for moving hydrogen from one reactor to another reactor, or you can also use some kind of compressor or pump to move hydrogen from one to one. So depend upon your conditions, you can able to utilize the technology, choose the technology either using pump or the pressure differences. And we also studied this energy storage by using solid oxide fuel cells. The same one. I'm not going to take this one. Okay, so yeah, so the same system, instead of PEM fuel cell, we have also studied about the solid oxide fuel cell, how we can able to utilize this kind of system for the stationary applications. So as I said, compared to PEM, because the low temperature output we are not able to use, but in this case, if you have 700 or 1000 degrees centigrade, you can able to utilize that waste heat which is coming from the PEM, like solid oxide fuel cell. Again, you can supply to the Rankine cycle, or organic Rankine cycle or Brayton cycle. You can improve the efficiency, so that the total efficiency we are increasing much. Okay, so these are the graphs for improving the efficiency, and we also studied about hydrogen product storage using natural graphite. Here you can see that the analysis of the Trigen system by using solid oxide fuel cell and metal hydride, and also using some kind of Rankine cycle, and the waste heat is taken from vapor absorption cycle. So in this way, you can able to achieve high efficiency, like reduce the waste heat. Yeah, so whatever the waste heat is coming from solid oxide fuel cell, either you can give to organic Rankine cycle, or you can give to absorption chiller, so that you can improve the total efficiency of the system. Yeah, so this yeah. So with this, yeah, so last topic is, we have also designed one integrated beam down technology with copper and coal cycle. So initially I have explained how we can produce hydrogen through electrolysis. There is another one is thermochemical hydrogen production, where we can use the different cycles to produce hydrogen, but the input energy is in terms of thermal energy. So you need some cycles, copper chlorine, we have to give at least 540 550 degrees centigrade, whereas sulfur iodine cycle you have to give 900 degrees centigrade. So for that, how you will get this heat, that is very important aspect to design this kind of hydrogen production system. See, here we have designed one integrated beam down system, where we can get very high temperature by using the solar dish. Okay, then you are able to give this thermal input to the copper gold cycle. You can produce the hydrogen. That is the advantage of this kind of system. You can able to use solar energy, thermal energy, then you can able to produce the hydrogen instead of solar PV plus electrolyzer. There you can produce hydrogen, but other way, using solar thermal technology, produce heat at very high temperature, that will give to thermochemical cycle, where you can produce hydrogen. Yeah. So with this, I'm stopping. Thank you. Yeah.
Thank you, Dr. Satya Sekhar, sir, for given this various metal hydride technologies on the storage and different factors. Probably it carries some good message to the participants. Now it is a question and answer. Yeah. So if you have any questions, please you can have have a question with Dr. Satya Sekhar.
Good evening, sir.
Yeah, good evening, sir.
Sir, this is Suresh Kumar from AICTE University, Hyderabad.
Yes, sir.
Sir, it's a very excellent talk, sir. Actually, we got so many insights about hydrogen storage and thermal storage energy systems, sir. Basically, I want to have a small question is there, sir. Like
Please, sir,
actually in
please.
MH based hydrogen, this one, what are the research avenues? Actually, one thing actually you told that thermal conductivity is one of the issues.
Yeah.
What are the other research avenues in MH-based hydrogen storage, sir?
You see, MH will be used for only special cases. You cannot use all the transport applications, but you can use some cases like forklift, where you need a ballistic weight, like supporting weight is required to support your forklift. In that
Yes,
case,
sir.
your metal hydride can be added advantage, because it will give hydrogen storage, and also it is giving some weight, so that this weight we can decrease the ballistic weight other side. So this kind, and you can also use for underwater autonomous vehicles, where you need some kind of buoyancy. The weight will be added advantage using the metal hydrates. Like that, you can go like choose type of applications where it will fit metal hydrates into that hydrogen storage.
Sir, actually, I wanted to know like thermal conductivity is one of the issues, like that, and another one is actually optimization of the reactor.
Yeah.
And what are the other research avenues in that particular area? I'm just asking.
Research area, like you have to optimize the again Li. So because your
New materials, new alloys,
new materials,
and
and it will
characterization,
depend upon your pressure and temperatures of your application. Based on your application, you have to choose which material will give the exact pressure and the temperature. That will give the good fitting with respect to your integration.
Okay, sir. Thank you very much, sir.
Yeah, thank you, sir. Yeah.
Hello, good evening, Dr. Satya. It was very interesting presentation and very, I think, quite informative on covering almost all the aspects of metal hydride. I just
Yes.
have a question. I mean, of course, for automobile applications, I think metal hydride is out of question because of the weight. So, may I know per kg of hydrogen storage, what would be the typical weight of metal hydride storage system? I mean, typical or a range.
Sir, yeah, with metal hydrides we can go up to 5-8%. Like 5 kgs means you need at least 100 kg of metal hydrides. Yeah.
So you mean
Yeah,
per
that's what
kg of,
I said. So you cannot go for like every applications using metal hydrides, but some applications very specific. This may not be penalty for those applications. Suppose stationary, you don't have any weight problem, but you can have advantage of volume, which is less in terms of metal hydride, and
Correct.
operating conditions also will be very much suitable in terms of safe stationary conditions, where you don't need to compress,
I
or
think
you don't need to liquefy hydrogen, so that you are saving a lot of energy in terms of compression or in terms of liquefaction. Like you have to choose, you have to tailor made, depend upon your application. You have to go for the different kind of storage systems.
okay. Uh, Regarding this MH compressors,
Yeah.
I think I came to know about this for the first time today, and it was very interesting. Where we can generate a pressure about 200 bar. So compared to conventional compressors like hydrogen compressors, what would be the energy? I mean, energy comparison in terms of let's say per kg. If you have 1 kilogram of hydrogen, want to compress from atmospheric pressure to 200 bar using conventional compressor and metal hydride, what would be the typical energy requirement?
Yeah, sir. Actually, I have shown only 200 bar, but people have, we have developed up to 200 bar, but people has compressed up to 400 bar using MS technology. So here the advantage is MH, you are using only low grade heat, which may be solar energy or which may be industrial heat. See here, the efficiency may not important if you have like a waste heat or if you have a
Okay.
solar
Yeah,
thermal energy. But
understood.
efficiency wise, obviously it is less than mechanical compressor. But
Mm.
adding advantages, suppose you can able to use waste heat, and also like safety operation, also safety wise also it is very good in terms of you don't have any moving parts in this.
Yes, yes. Safety wise, I think probably
Yeah.
metal hydride are the safest one among all, as far as I understand.
Yes. Yeah.
Yeah. Thank you so much. Thank you. It was
Yeah. Thank you,
very
sir.
informative and interesting session. It
Yeah.
would be
Thank you, sir.
great if you
Thank you.
can share the PPT for our knowledge. Of course,
Yeah.
just for
Sure, sir.
our
Sure, sir. Sure, sir.
yeah. Thank you. Thank you so much.
Good evening, sir. I'm Anushka Kulkarni, a research fellow from VJTI Mumbai.
Yes,
I
ma'am.
was
Please.
working on net zero emission. So
Okay, ma'am.
I had a doubt when you mentioned about carbon nanotubes being used for storage. So if we are using carbon nanotubes, how are we going to deal with the hydrogen reaction with carbon?
Yeah, actually, I have shown that what are the technologies available, but people are not using practical applications with respect to carbon nanotube because we need cryogenic temperature. So getting 77 Kelvin is not easy task to store the hydrogen. It is not practically applicable. So in practical cases, no one will use carbon nanotubes, but uh, because some research is done, just I'm saying that this is also one of the storage media to store the hydrogen. But in practical cases, either people use compressed storage or liquefied hydrogen related to space applications, or like metal hydrates will be used for stationary applications, and some station like maybe forklift or some underwater vehicles we will use. Yeah.
Okay, thank you so much, sir.
Yeah. Thank you.
Good evening, sir.
Yeah. Please.
I'm Tania Ghosh, Assistant Professor of Arkajan University, Jharkhand.
Yes, madam.
Sir, thank you. Thank you. It is a very informative session. Thank you so much. My question was same. अनुष्का कुलकर्णी मैडम का क्वेश्चन ही मेरा क्वेश्चन था. Thank you, sir.
Yeah. Thank you.
Sir, can I get the PPTs?
Yes. I will share to Professor Iswarmurthy, so he will share to all the candidates.
Okay. Thank you.
Good evening, sir.
Yeah, please, sir.
This is Dr. Akashdeep from Lovely Professional University, Jalandhar.
Okay, yes,
First
sir,
of all,
please.
sir, very nice and informative PPT. I really appreciate that. But my question, sir, is a little bit different. But just I want this is just my curiosity that you have somewhere talked about the storage possibilities, right?
Yeah. Yes,
So
sir.
through metal form and some other materials. So my curiosity developed is that rather than complete storage, can we have a partial storage while supply of hydrogen to some other passage? Like I want to send the hydrogen controlled hydrogen amount to the engine, right?
Yeah.
So that needs too much control over the flow rate.
Yes.
So can we place such material in between the passage so that we can precisely control the flow rate during the engine flow to the engine?
Yes, you can do that. But why we are using this kind of foams as a explained earlier? This thermal conductivity of metal hydride is very low, 0.5, 0.4. So with that 0.4, 0.4, you cannot get what you need the heat transfer rate. If you don't have heat transfer rate, then again that same problem will for an absorption desorption, because if you don't have remove that heat or added heat at proper time, then your pressure also will increase, so that your driving potential will come down, so that your reaction will stop.
Okay, so that means
To
if we
maintain
want
that,
to, if
to
I want
maintain
to
that pressure
use this,
limits.
along with that, I need to take care of the heat transfer rate in accordance with the flow rate of the hydrogen
Yes,
out of the cylinder.
Yeah, yes, exactly. Yeah.
Okay, so I need to separately optimize that also. Like, with respect to flow rate, what would be the heat transfer requirement? And for you have talked about the storage heat transfer rate during
Yes,
the
yes.
storage.
Yeah, yes.
Okay, thank you, sir.
Yeah, thank you. Yeah.
It's a time, it's 9 o'clock. I think we can close this session. So it is my responsibilities to express my sincere thanks to Dr. Satya to accept some modification. He is supposed to join today in the last session and tomorrow more first session. He joined what do you call it, another based upon our the previous speaker things. So it is very kind of you, sir. I thank you so much. On behalf of my university, I express my sincere thanks to you.
Yeah, thank
Thank
you
you,
so much,
sir.
sir. Thank you so much.
I thank all the participants who joined on time, but I expect tomorrow, please, you join before 6 o'clock. It will be great help for me. So you are maintaining good discipline. It's try to keep it up. So we will update you that attendance sheet and the recorded video by tomorrow morning. The feedback will be send it to you at 9:30 or 9 o'clock. Please, you can give the feedback about today's sessions. So thank you. Thank you, one
Yeah,
and all.
thank
So
you
thank
so much,
you.
all the participants. Yeah, thank you.
Yeah,
Good night. Yeah.
thank you. Thank you. Good night. Good night. So formally, we are closing our day 2 session 4. Thank you. So video so stop करो, recording stop करो. Network sender, would you stop the video recording?